Okay. All right. A very good evening, all. So in the yesterday's session, we have started the course Power Electronics, and we discussed about the concept of switch, right? What is the difference between the ideal switch and the practical switch, right? Now let us discuss this numerical. Find the average current and RMS current for the current waveform shown in figure. Okay. Intentionally here, I have taken the peak value of this triangular waveform as a capital A, right? Because it will be, if this is a generalized, that is the capital A, then we can write the expression in the generalized way. And that will help you in finding the power loss in the switch, right? So my first question is whether this current I is a periodic or not. Come on, whether this current waveform is a periodic or not. Periodic. Okay. Some are saying periodic, some are saying not. Okay. Let me first tell you how to find whether the given waveform is a periodic or not, right? So here you can check. Actually, this is a continuous waveform. Whatever the waveform varying from 0 to t, the same will repeat from t to 2t. Same will repeat from 2 to 2t to 3t. Okay. So here after this 4t by 3, again we will be having till 2t, we will be having the 0 period, 0 current, and after that again the same cycle repeats. Actually, this is the periodic waveform. What is the periodicity? The periodicity of this waveform, yes, is capital T, right? Capital T. Periodicity means time taken to complete one cycle. That is nothing but the periodicity. So here periodicity is capital T. Periodicity is equal to capital T, right? Now our task is to find the average value and the RMS value of this current waveform. So we know now average value, how to find average value? It is a 1 by T integration over 0 to T, that current I into dt. But the integration means what? It is the area, na? Right? So we have written, if you recall, we have written the same thing for the average value. Yes, here it is. Average of y is equal to what? 1 by T, this integration over 0 to T f of t dt. In the study session, we discussed this. And this integration indicates the area, right? So here can I write for this I average is equal to 1 by T into area of this, right, curve or of this triangle here. So what is the area here? So it is equal to 1 by T into, yes, area is 1 by 2 into this length. It is a T by 3, right, into this height, that is the A. So if you check, it is equal to, we can write it as a, yes, T will get cancelled out. So it is like A by 6, right? This is a I average. Calculating the average value is very easy because we know it is a 1 by T into area, right? 1 by T into area. That's it. Okay. Now, next is how to find the RMS value. How to find the RMS value, right? So for that, let me write IRMS. Yes. First of all, let me simplify it by using the expression of that waveform, and at the end we will discuss what will be the final expression. Okay, so that it will be easy to memorize that expression, right? So it is a 1 by T integration over 0 to T current I square na into dt to the power 1 by 2. RMS square root of mean of squared value. So this is the 1 by 2 means root to the power 1 by 2 means it is a square root of mean of squared value. We are squaring it na, right? So integration of 0 to T I square dt and 1 by T into 1 by T, it indicates it is the average of the squared value, right? Average of the squared value. And again, we are putting it into the under root. So that's why it is a root mean square root of mean of squared value, right? So let me simplify this, which is equal to, yes, 1 by t, we can write it as integration over 0 to t by 2 current I. Let me write it as a I square into dt. Instead of t by 2, we're having t by 3, na? Right? We're having a t by 3, right? Next, plus integration from t by 3 till t. What is the current? 0 into dt. Means this 0 to t interval I have divided into 0 to t by 3 and t by 3 till t. Definitely this integration will become 0, because integration of 0 will be 0 only, right? The thing is, we need to, yes, simplify this expression. So for that, we need to, yes, replace this small I with the expression, right? With the expression of this, right? Expression of this curve. Now, how to find the expression of this curve? We will discuss this in the yesterday session. Yes, it is a linearly increasing. So slope will be, it is a change in a y divided by change in the x. So change in the y, let me write it as I is equal to change in the y, that is a divided by change in the x is t by 3, right? A upon t by 3 into, it is a t, right? A upon t by 3 into t. This is the expression for the current. Now we can simplify here, we can put here that I, right? So it is equal to 1 by t to the power 1 by 2 should be here, right? Yes. 1 by t. Next, it will be like integration over 0 to t by 3 I square, but I is nothing but your a divided by t by 3 into t, right? Bracket square into dt to the power 1 by 2. Yes or no? Right? So it is a t divided by t by 3. A into t divided by t by 3, right? So I have written here a into t divided by t by 3 square, right? Next, so we need to simplify it. So from this we can write, yeah, so it will be like a square divided by t square, okay, into, this is a t by 3 na, so let me write it as t by 3 square into, yes, integration over 0 to t by 3 t square into dt whole to the power 1 by 2, correct? So here I have taken, yeah, this should be the t only, right? Right. Okay. So a square I have taken outside. This t by 3 square I have taken outside. This t will remain as it is, and this t square into dt. What is the integration of t square? It is a t cube by 3. So let me write it as, which is equal to, yes, a square divided by, let me write it as t into t by 3 square into, that can be written as a t cube divided by 3, right? 0 to t by 3, correct? To the power 1 by 2, right? To the power 1 by 2. Further, we can write it as, which is equal to a square divided by, yeah, t into, let me write it as t by 3 square into, this can be written as t cube divided by 3 cube, okay? T cube divided by 3 cube. So it is a 3 cube is nothing but 27 into 3, right? Whole to the power 1 by 2. So further we can simplify it as is equal to, you can check here, this is a 3 square, here it is a 3, okay? So 1 3 will get cancel out, right? So we can write it as a square divided by, this is a t square into t, that is a t cube, this t cube will get cancel out, right? So t will like, I can write it as a divided by 27, right, divided by 9, 27 divided by 9, right? So which can be written as a square divided by 3, right? A square by 3 to the power 1 by 2, the power 1 by 2. Am I not audible? Am I audible or not? Some students are saying this.
Hello.
Yes, please.
Sir, please try to use a sketchbook, sir. Sir, here PDF, the PDF you uploaded yesterday was completely distorted, sir.
What you are saying?
Sir, PDF you uploaded yesterday of yesterday class.
Yes.
Sir, the pages were ऊपर नीचे थे सर वो.
ऊपर नीचे नहीं था एक्चुअली. क्या है कि वन नोट टू जब मैं पीडीएफ कन्वर्ट करता हूँ, इट हैज एक्चुअली इशू.
सर आप स्केचबुक तो यूज कर सकते हैं, इसमें एक्चुअली
मैं देखता हूँ
व्यूइंग
मैं
एंगल भी काफी
स्केचबुक.
कम है.
यस यस, एक्चुअली मैं देखता हूँ स्केचबुक का ये कर रहा हूँ मैं. राइट.
ओके ओके सर.
ओके.
Hello, sir.
यस यस.
Sir, actually, morning sessions are going now, sir. T and D.
व्हाट?
Uh, actually, in schedule, it is showing morning sessions for us. T and D, transmission and distribution.
Yeah, it is morning. For morning session, you are having the T&D.
Sir, how can we attend, sir, morning session? Because we are having colleges, sir. How can college going students can attend morning sessions?
Actually, better if you contact the office person, right?
Sir, we contacted the office person, sir, but he is saying that all the students are agreed for that. May I know that which persons are agreed for that, sir?
Okay, I will communicate your message to them. Okay. Yeah. Yes,
Hello, sir.
Nagu. Yeah. Milan Kumar, do you want to say something?
Sir, in average value.
In
average value.
Okay.
Why put the 1/2?
Okay, it is 1/2. No, it is simply the area, na? How to find the area of the triangle? This is the area, na?
Yes.
So how to find the area of the triangle? It is a 1/2 into this length into this length.
Okay.
All right. Okay.
Okay. Then.
Yes. Just a minute. Let me check why the students have reason. Yes, Pawan Kumar.
Sir, no one is.
Yes.
No one I talked to you, sir.
I am not getting what you are saying.
No one I talked to you, sir, regarding the classes.
Morning session you are saying?
Yes, sir. Yes, sir.
Okay. ठीक है. I will discuss with the Seshu. Okay. Yeah. Milan Kumar, do you want to say something? Please unmute yourself. Yeah.
No, sir. Continue.
Okay. Because the problem is continuously I am getting the message, and in this class we are having almost more than 500 students, and at the end if I check yesterday the total message count was around 1000. Okay, so if the continuously messages are there in the inbox, then for me it is difficult. That means I'm thinking that whether the students are having any doubt or like that. Okay, so that's why it is interrupting the class. Okay, so every doubt we'll discuss at the end of the session only, right? Okay, so yeah, so this is the thing we are having here. The time period is t by that is the function period. It is a t/3, and what is the periodicity? It is a capital T. Okay, so in that case actually we are getting average value is very simple. It is a 1/2 into area, right? Area A. Next, and here you can check This is a RMS value. This is a RMS value, right? RMS value. Okay, a square by 3. And you can check whatever the yesterday we discussed by using that expression also. If you find, we'll be getting the same answer in denominator 27 into 3 by 9. No, it's a 3 square, na? Yes, no, right? So that's why I have written it is like a 27 into 3 by 9. Okay. Yeah, correct. Yes. So it should be 9. It should be 9, right? So further, if you check the yesterday's expression, whatever we have written, from this we can write IRMS is equal to what? It is a square divided by 3, na? Into we wrote it is a function duration. Function duration, it should be 27 divided into 3 by 9, na? Right? 27 into 3 by 9. So it is a function duration divided by periodicity, na? To the power 1 by 2. So you can check here. The function duration is t by 3 now, and the periodicity we are having, it is a t. So if you put here like a t by 3 and here it is a t, you will be getting like again a square by 9 only, right? So always keep in mind, if the signal is a triangular, okay, then how to find the RMS value? It is simply a square by 3 into function duration. Function duration means this I am saying. This is a function duration, right? And this is a periodicity. Okay, so like this, correct? So next, let us discuss for the rectangular function. Find the average current and RMS current for the current waveform shown in the figure. Okay, so for this waveform, we are required to find the average and the RMS value. So how to find the average value? We are having the standard average is equal to, again here I have taken the magnitude is equal to capital A, right? So average is equal to what? It is a 1 by t into area, na? Area under the curve. So you can check here, which is equal to 1 by t into what is the area? It is a t by 2 into A, right? So it is a A into t by 2. So if we simplify it, we'll be getting it as equal to, yes, A into tt will get cancelled. So it is equal to A by 2. This is the I average. That is the average value of current, right? Rectangular shape they have given. Okay, means for average value, we are using only this expression for all the functions. Okay. Second, how to find the RMS value? We can write RMS value is equal to, yes, it is a 1 by t. You can check here. We are having the periodicity is capital T, and during 0 to t, we are having the two intervals, na? 0 to t by 2 and t by 2 to capital T. Between t by 2 to capital T, it is a 0, right? So effective interval is only 0 to t by 2, right? 0 to t by 2. So let me write it as 1 by t integration over 0 to t by 2. It is a square into dt to the power 1 by 2. I am taking the average of the squared value and putting it into the square root. Please try to understand this. Square root of mean of squared value. Okay, so we can write it as is equal to, yes, it is a square divided by t into integration of 1, that is a t, and limit will be 0 to t by 2 to the power 1 by 2, right? So let me write it as is equal to a square into, can we write it as t by 2 upon t to the power 1 by 2. This is a IRMS. So in general, can we write the expression for RMS value of a rectangular function, of a rectangular, or you can say the square signal, okay, is IRMS is equal to a square, right, into what is t by 2? T by 2 is your, yes, function duration. Okay, it is a function duration divided by this t is nothing but what? It is a periodicity. Okay, periodicity to the power 1 by 2. Is this clear? So for triangular function, it is a square by 3 into, yes, function duration divided by periodicity. For the rectangular signal or the square signal, okay, square means this type of signal I am saying, where the negative pulse is not there. Okay, so for this type of signal, yes, we are having a square into function duration divided by periodicity to the power 1 by 2. Okay, simply you can memorize it. Simply you can memorize it. Okay, next, or if you don't want to memorize this, yes, you need to simplify by using this expression like this: square root of mean of squared value. Okay, so next, let us check for this question. Now here we are having the current waveform. It is the combination of, yes, triangular, and here it is we are having the square type function. Okay, so how to find the RMS value of this current, IRMS? So simply here we need to use the superposition theorem, just like a superposition concept. What is the superposition? Means first of all consider this one, at that time neglect this, second time consider this one and neglect this, like this we need to consider. Are you getting the point? Okay, so how to write the RMS value? IRMS is equal to, what is the periodicity? It is a T, na, right? So let me write it as a, yes, for the triangular function first. Okay, for the triangular function, what is the RMS value? How to find for the RMS? How to find the RMS value of the triangular function? It is a square divided by 3, right? So let me write it as, this is a 10, na? So in our case, a means what now? 10. A is nothing but 10, na, here, right? So let me write it as a 10 square divided by 3 into, what is the function duration? T by 2. So into T by 2 divided by, what is the total time? That is the periodicity. It is a capital T. This is for, yes, triangular only. This is for triangular only. Next, find the RMS value for this function now, right? That this square function. So how to find here? We know it is a square, na? It is a square, right? So a is now here in this case minus 10. So it is a minus 10 square into, for this function, yes, what is the that multiplication? A square into function duration. That is function duration is T minus T by 2, means this much, na? Right? So it is a T minus T by 2, means T by 2 only. Let me write it as T minus T by 2 divided by, what is the periodicity? It is a capital T again to the power 1 by 2. Please try to understand here. Yes, this indicates for triangular function, right? This is for triangular. This one is for, yes, your rectangular. Are you getting the point? Okay, and again simply I have added these two. Simply I have added these two, right? So if we simplify it, we'll be getting it as is equal to, it will be like a 10 square. Let me take 10 outside. So it will be like a 10, right, into, here we can take T square also outside, right? T also we can take outside. So it is a under root T into, it is a T by 2 plus T minus T by 2, that is a T by 2 to the power 1 by 2, right? So it will be simply, it is root T will get cancelled out. So it is equal to 10 ampere, right? So it is a 10 ampere RMS value. Check once. Just a minute. This divided by 3 I need to take, right? So this should not be 10, right? This divided by 10 we need to consider. Okay, so it is like a 10 by root T into, it is like a T by 2 plus 3T by 2. Okay, so it is like a 4T by 2 divided by 3, na, to the power 1 by 2. So you can check here, this root T and this root T will get cancelled out. Okay, so it will be like a 10 into, this will be 2 by 3. So it is like a to the power 1 by 2 here. So it is a 10 into under root 2 by 3. This is your IRMS. Correct? Means here what I have done, I have calculated the RMS of this one, right? Next RMS of this one simply, right? So this is the one expression, this is the second expression, and we have just put it into the square root. This is the one way. This is just like a shortcut way. Or the second option is we need to write the expression for this waveform, right? This is a straightforward. Now this is a constant. Okay, so no need. We are not required to write the expression for this one. Okay, and how to find the RMS value? It is a 1 by t integration over 0 to t. This expression square into dt plus integration from t by 2 to t. It is a minus 10 square into dt and whole to the power 1 by 2. In this way also you can simplify. You will be getting the same answer. You will be getting the same answer. Are you getting the point? Right? So means it is a combination of triangular and the rectangular function, right? Next. Let us discuss this function. This is a Cauchy square wave. Okay, this is a Cauchy square wave. Generally, this kind of output you will observe in a rectifier circuit for the input current waveform. Okay, input current waveform, and as well as for the inverter circuit for the output current waveform. Okay, you can observe this kind of waveform. So now in this case, this is a Cauchy square. Let me write here, Cauchy square wave. Cauchy square means it is like a square wave only, but it is having in between zero intervals. Right? Now, how to find the RMS value of this type of waveform? Okay. So here, first of all, let us simplify it by by using our expression, and at the end we will conclude it. Okay. So how to find the RMS value? IRMS is equal to, whatever the waveform will be having from 0 to 2 pi, same will be repeating from 2 pi to 4 pi. Okay, so the periodic angle here, okay, so it is equal to 2 pi, 1 by 2 pi, right? So in the 1 by 2 pi, we are having total 4 intervals, 0 to alpha, alpha to pi, pi to pi plus alpha to 2 pi. Yes or no? Right? So here let me write, it has a integration from 0 to alpha, it is a 0 now, into d omega t. This is the angle, so definitely it should be the omega t here, right? Omega t. So 0 into d omega t plus integration from alpha to pi. What is the value? It is a square into d omega t. We are finding the RMS, so that's why I have squared it. Okay, plus integration from pi to pi plus alpha. What is the value pi to pi plus alpha? It is a 0 into d omega t plus integration from pi plus alpha to 2 pi. What is the value? It is a minus a, minus a square into d omega t to the power 1 by 2. Right? Square root of mean of squared value. We have squared it. So integration of 0 is 0. Here also integration of 0 is 0. The only thing is this term and this term will be non-zero. Right? So we can simplify it, which is equal to IRMS is equal to 1 by 2 pi into, we can write it as a, can we take this a square outside? Yes, right, a square outside. So it is a square divided by 2 pi, a square divided by 2 pi into, let me write, what is the integration of this? It is omega t. Omega t, limit alpha to pi, right? Plus integration of this term, a square we have already taken outside. Okay, so integration of this term, it is a omega t only. Limit pi plus alpha till 2 pi to the power 1 by 2. Right? So further we can write it as is equal to a square divided by 2 pi into, put the limit. It is like a pi minus alpha, right, for this term, plus 2 pi minus pi minus alpha, okay, to the power 1 by 2. So this can be written as pi plus 2 pi, right? So it is like pi minus alpha, and this is also 2 pi minus pi. So it will be a pi and pi minus alpha, right? So we can write it as a square divided by 2 pi into, yes, it is like a pi minus alpha plus pi minus alpha. So it is a 2 pi minus 2 alpha. So 2 into pi minus alpha to the power 1 by 2. 2 will get cancel out. So can we write it as is equal to a square into pi minus alpha divided by pi to the power 1 by 2, right? So how we can write this in generalized way? Yes, let me write it as, this is a IRMS actually. So in general way, we can write it as, yes, IRMS for a Cauchy square wave, is equal to a square into, yes, this is a pi minus alpha, means what? It is a function period. Okay, it is a function period. Function period. Or the, yes, function duration, you can say. Function duration. We have used the word duration, right? So function duration divided by what? You can check, it is a pi. Our periodicity is 2 pi, na? Our periodicity is 2 pi. But here we are getting divided by pi. Divided by pi, the meaning is it is a time corresponding to, or the angle corresponding to the half cycle, na? Right? Half cycle time. Half cycle. If the on the x-axis, if you are having time, take the time. If the angle is given, then we need to consider the angle. Is this clear? So function duration divided by half cycle. Let me write it as an angle to the power 1 by 2. So you can check what is the function duration here. Function duration is, yes, from alpha to pi, na? So it is a pi minus alpha. This is a function duration, right? And what is the half cycle corresponding angle? For full cycle, angle is 2 pi. For a half cycle, the angle is pi only, right? So in general way, we can write it as IRMS is a square into function duration, right, divided by half cycle angle. This function duration means it is again angle only. If in the denominator you are having angle, definitely here also in the numerator we are expected to put the angle only. Is this clear? Right? So it is a square into function duration divided by half cycle angle. So till now we discussed the first one is for rectangular function, first one is for triangular function, next rectangular function, and next we discussed for the Cauchy square wave. Yes or no? Right? Yes. Vikrant, you want to say something? Okay. So is this clear? Next, let us discuss next one. Find the RMS current for the current waveform shown in figure. Okay. This is a square wave we are having. This is a square wave. Means we are having the positive cycle, positive cycle, and negative cycle. Okay. So it is a square wave. So how to find the RMS of this? Okay. So first of all, let us simplify it, and at the end, we'll write the conclusion. Okay. So IRMS is equal to, yes, it is a 1 by 2 pi. Let me write integration over 0 to pi, value is a na, so it is a square into d omega t plus integration from pi to 2 pi. It is a minus a square into d omega t whole to the power 1 by 2. Yes, no? Square root of mean of squared value, right? So 0 to 2 pi interval I have divided into 0 to pi and pi to 2 pi, right? So next we need to simplify it. It is equal to a square divided by 2 pi, a square divided by 2 pi into, yes, we can write it as a integration of this a square were taken outside. So integration of 1 will be omega t, limit, let me write it as in this way. Okay. it is a 0 to pi plus integration of 1 is again omega t, pi to 2 pi, and whole to the power 1 by 2, correct? So let me write it as a square divided by 2 pi into, this will be like a pi minus 0, correct, plus 2 pi minus pi to the power 1 by 2. So if you check, it is equal to a square divided by 2 pi into 2 pi minus pi, that is a pi, pi plus pi, 2 pi, okay, into 2 pi, right, to the power 1 by 2. So can we write it as is equal to 2 pi gets cancelled out, so it is equal to a. So this is a IRMS. So always keep it in mind. If the function is a square wave, if the function is a square wave, then the RMS value is nothing but, yes, is nothing but the magnitude of that waveform, right? It is a P, RMS, the value is A, na? So RMS value is A. You can check, na, RMS means what? Square root of mean of squared value. So we are first of all squaring the instantaneous values and we are taking the average. So if I take the, yes, if I take the square of these instantaneous values over 0 to pi, what is the square? It is a square. Over pi to 2 pi, what is the square? Minus a square. Minus a square is again a square. So if I draw the waveform for the I square, if I draw the waveform of the I square, then it will be like a square, and here it is also a square, means we will be getting a square waveform, that is the flat waveform which is having a magnitude of a square. Yes or no? So what is the average of that a square waveform? It is a square only, right? So average of the squared value is we are getting it as a square, and put it into the square root, you will be getting a only. You will be getting a only. So for square waveform, yes, keep it in mind, the RMS value is nothing but the magnitude of that waveform, right? So for square waveform, RMS value, let me write it as IRMS, is equal to, yes, it is a which is equal to magnitude of, yes, magnitude of waveform, or you can say the magnitude of that signal. Okay, so we have discussed the total cases, just like first one is the triangular, second one is the your rectangular, right, third one is the quasi square wave, and fourth one is the square wave, right? So these are the general cases we have discussed. Okay, in the triangular, if you recall, in the triangular case we have written, yes, here IRMS, this is for triangular only. Let me write, this is for triangular wave. Okay, so if the given signal is triangular, then RMS is equal to a square by 3 into this function duration divided by periodicity. Next, for rectangular, yes, we are having this one. You can check, rectangular means this type of signal, right? Only positive, negative is 0. Okay, so it is for rectangular. Next, quasi square wave. Okay, this is a combination actually we have written, right? For combination, we need to use that. In this case, it is a triangular and the rectangular combination. Okay, next, here, this one is for quasi square wave, right? This is for quasi square wave. And the last one is for square wave. Okay, so this is for square wave, right? So these are the cases we have discussed. Okay. Yeah, you can say A as a amplitude. Okay. Okay. I will take it slow. I'm being so fast. Is this clear? So we're having total, I have discussed total, yes, 4 types of the waveforms here we have discussed. Okay, simply go through it, and in your running notes, please note it. For triangular, what is the expression for the IRMS, so that during the final examination, it will save your time. Okay, it will save your time. Otherwise, what we need to do, you need to write the expression for that particular waveform, and we then simplify it by using that RMS, right? Square root of mean of squared value, means integrate and those things. Okay, so these are like some shortcuts. Okay, so generally some students thinks that, sir, we are having total for engineering, if we consider just like in university examination subjects. Okay, so for GATE we are having almost around 20 subjects. Okay, so how to, sir, memorize all these expressions and those things? So in that case, my suggestion is that if you are feeling difficult to memorize something, okay, then simply be strict with your basics. Okay, these basics are very important. Square root of mean of squared value. Okay, right. Next, now let us move towards the next point. Piecewise modeling of switch during on state and conduction state power loss. Okay, now we are going to discuss the how the semiconductor switches are modeled during their on state. Okay, are modeled during their on state. So be careful here. During on state only we are discussing. Okay, and depending on that, we are going to write the expression for what is the on state power loss, okay, of that particular switch. Right, very important discussion. So piecewise modeling of switch during the on state. Okay, so we know when switch is in a on state means it is generally represented like this. Okay, this is a, this is a B, right? So the switch is going into the on state. Okay, so in the piecewise modeling, any semiconductor switch is modeled or represented, okay, in 3 general forms. In 3 general forms. Okay, which are those forms? First one is in form of resistor. This is a, this is a B. This is R is nothing but this is a on state resistance, R on. That is the on state resistance of that switch. The second model is, yes, second model is, yes, it is in the form of voltage drop. Okay, on state voltage drop. That is a, let me write it as a VT. This is also a switch. A and B terminals means are the terminals of the switch. Terminals of the switch. When switch is in an on state, when the switch is in an on state, either it can be represented with a R on. It can be either represented in terms of on state voltage drop, or it can be represented as combination of voltage drop and resistor. Okay, so like this, resistor and voltage drop. So this is a, this is a B, this is a R on, and this is a voltage drop, that is a VT. Okay, voltage drop, that is a VT. So I'm repeating, piecewise modeling of the switch during the on state means every switch during its on state, okay, is represented with its equivalent model. Okay, and that equivalent model, yes, it will be either this one, that is only resistor, or this one, that is only on state voltage drop, or this one, that is a combination of on state voltage drop and the on state voltage drop and the on state resistance. Okay, now let me write here, generally the MOSFETs are represented with on state voltage drop, that is on state resistance. Generally the MOSFETs during their on states, okay, are represented with equivalent resistance only. Why MOSFETs are represented as an equivalent resistance, that you will understand while discussing the MOSFET. Okay, so keep it in mind. If the MOSFET is there and if the MOSFET is in an on state, okay, I can simply replace that MOSFET, yes, equivalent to this on state resistance. Second thing, yes, we are having the equivalent circuit, or the modeling is, yes, this voltage source. Generally the BJTs, generally the BJTs are represented during their on state, okay, as equivalent to the VT, that is a on state voltage drop, on state voltage drop, right? And next, this, that is a combination of on state resistance and on state voltage drop, okay. Generally the switch like a SCR, we're having a diode, right? We're having a IGBT, we're having a GTO, right? These switches are represented during their on state with this type of model, with this type of model. Are you getting the point? Let me write here: SCR, diode, IGBT, and GTO. And GTO. These are represented with this type of model. Is this clear? Means any switch you can consider from in the power electronics, whatever the switches we are going to discuss, okay. When the switch is in a on state, that respective switch, if the switch is BJT, then during on state we can replace it with this circuit, okay. Why it is represented like the constant voltage source only or the voltage drop only, that you will understand while discussing the BJT. Actually it has a relation with that characteristic of the BJT, right? That characteristic of that particular device, particular switch, okay. So keep it in mind. For MOSFET, it is represented with a on state resistance during on state, I'm saying, okay. BJT represented with its on state voltage drop VT, that is the constant voltage. And yes, SCR, diode, IGBT, GTO, these are represented with on state resistance and a voltage source VT and a voltage VT, that is a voltage drop VT, right? Now when the switch is in a on state, definitely the current will flow like this. Yes or no? Let me write this current as I. Let me write this current as I. Okay. So this is a I. So definitely in these models also, we need to indicate this current as a I only here. Because when switch is in a on state, definitely the current flowing through the switch will be non-zero now, right? So if current here is I, definitely current here is also I. Definitely current here it is also I. And definitely current here it is also I. It is also I, right? Now we are going to write the on state power loss. It is also known as the conduction loss, okay. We are going to write the on state power loss expression, okay, for all these three models, okay, for these three models. Are you getting the point? Means our task is to write the switch power loss, that is the conduction loss, okay, for these three models, right? So let me write first, yeah, on state power loss, on state power loss, right? On state power loss, or it is also known as conduction loss. It is also known as conduction loss, right? On state power loss, or it is a conduction loss, right? Next, so let us consider the first model, okay. First model we are having, it is only resistor now, it is a only resistor. So let me redraw it. Let me redraw it. So this is a R on, this current is I, okay, A and B. So how to find the power loss here, okay. So P, let me write it as a on, P on, that is a on state power loss, okay. Next, if the current flowing through the switch is periodic, current flowing through the switch is periodic, okay. What type of current will be there and those things they will give you in the example, okay. So power loss is equal to 1/T integration. What is the power loss in case of resistor? It is I square into R, na? Yes or no? I square into R. So it will be like a 0 to T I square into R on, 0 to T I square into R on. This is means what? We are I square into R1 means what? It is your power. I am integrating the power means what? I am adding the power. I am adding the instantaneous values of the power. Yes or no? Right? And dividing with the periodic angle, periodic time. That is the periodicity actually. Okay. So 1/T integration of 0 to T I square into R1 into dt. Now what is the R1? R1 is a constant. That on state resistance is a constant. So R1 is constant. So let me take it outside. R1 into what? It is like a 1/T integration over 0 to T I square into dt. Now my question is, what this term indicates? Yes. What this term indicates? this term, what this term indicates? R1 is constant, no problem. But what this term indicates? 1 by t integration of 0 to t I square into dt. It is like an average of the squared value, na? Yes or no? Average of the squared value. So can we say that this is if this is the average of the squared value, so can I write this as I RMS square? Because RMS means what? Square root of mean of squared value. If I put here to the power 1 by 2, then it will be your RMS, na? Right? So if I remove that 1 by 2 means what? It is a I RMS square only. So let me write it as P on is equal to what? R on into I RMS square. I RMS square. So, or it is like P on is equal to I RMS square into R on into R on. Is this clear? So always keep it in mind. Okay. If then actually this expression is valid for a resistor. Okay. In all the circuits of electrical engineering, if you want to find the power loss in case of resistor, then while finding the power loss, we need to consider, yes, I RMS square into R only. It is not I average square. No, it is a I RMS square into R only. Is this very clear to all? Please try to understand this. I have replaced this term with the I RMS square, because we know na, I RMS means what? 1 by t integration of 0 to t I square dt to the power 1 by 2 is nothing but your I RMS. If I square it, then it will be like a I RMS square. Then we will be getting this expression actually, right? Without to the power 1 by 2 means what? It is I RMS square. So that's why it is P on is equal to I RMS square into R on. Is this clear? So always keep it in mind. In the case of resistor, the power loss, okay, is equal to RMS current square. RMS current means what? The RMS value of current which is flowing through that resistor. It's a square into resistance value, into the resistance value. Is this clear? Right? Okay. Right. Next. Now let us check for the second model. Let us check for the second model. Second model we are having only this one. Okay. So second model, power loss for the second model. Power loss or conduction loss, right? Second model we are having, it is like this. This is a, this is a B, this is VT, and current flowing is capital I, right? We have considered a capital I. Now, what is the power loss here? P on, this is the on-state power loss. The power loss means on-state power loss, right? Is equal to what? P on is equal to 1 by T integration over 0 to T. Now, what is the power here? Voltage into current, na? In the previous case, we consider I square into R because the resistance was there. But in this case, it is a voltage is there, na? So that's why voltage into current we need to consider. So it is a VT into I into dt, right? Now in this, what is a VT? VT is a constant, na? So we can take it outside. So it is equal to VT into 1 by T integration over 0 to T. This is a I into dt. So what the term, what this term 1 by T into integration over 0 to T I into dt indicates? This term indicates I average. Yes or no? 1 by T into integration 0 to T I dt means what? It is a 1 by T into area, na? So that is nothing but your average current. This term is nothing but your I average, right? So let me write it as, therefore P on is equal to VT into I average, right? Is this clear? Means in the case of resistor, it is I RMS square into R on. In the case of yes, if it is a constant voltage drop, okay, that's just like a BJT, then it will be like a VT into I average we need to consider. Third case, we are having the combination of the two. Third case is a combination of the two, right? So if the combination of the two, then what is the change? Third case, on state power loss for the third case, or conduction loss. On state power loss or conduction loss. In the third case, yes, we are having the third model as combination of resistor and a voltage source. This is a R on, and here it is a voltage drop, that is a VT. This is A, B, and this current is on state current, that is a capital I. So how to find the power loss? P on is equal to 1 by T, right? We can write integration over 0 to T. Now here we are having the two elements, na? One is the R on and second one is the VT. So what is the power loss here? It is a I square into R on, right, plus VT into I into dt, right? So you can check here. Yes, we can separate the integration here. So it is a 1 by T into, let me write, integration over 0 to T. It is a R on into, yes, it is a R on into integration over from 0 to T. It is a I square dt. This is the one thing. Plus, what about this term? Vt is a constant, na? So you can take it as Vt into integration from 0 to T. It is a I into dt. Correct? Again, this term, yes, this term indicates it is a, yes, if I take 1 by T, if I put the 1 by T here, then it will be like, let me write here. Yes. So it is equal to R on into 1 by T into integration from 0 to T I square dt plus, okay, this is the one term, plus Vt into 1 by T integration from 0 to T I into dt, right? This is the second term. So what this term indicates and what this term indicates? Can we say that it is equal to, this term is nothing but IRMS square and this term is nothing but I average. So let me write, it is a R on into IRMS square plus Vt into I average. This is the on state power loss, on state power loss, right? If the on state equivalent, okay, of the switch is combination of resistor and the voltage drop, then we need to find the power loss, on state power loss, by using this expression, I RMS square into R on plus Vt into I average. Okay, if the on state equivalent of the switch is only on state voltage drop, okay, then it is a Vt into I average. And if the on state equivalent of the switch is only on state resistance, then the on state power loss is equal to I RMS square into R on. That's it. Is this clear? Right? So these three are the, yes, expressions related to your conduction loss of a switch. I am using the word conduction loss. Conduction loss means what? When the switch is in a on state, okay, what is the power loss that is taking place in the switch? That is nothing but your conduction loss or on state power loss. Is this clear? Right? Now let us discuss some numericals related to this. Okay, numericals related to this. Yes, Shiva, P1 means this is the average value only. Okay, P1 means the average value. This is the average power only. Okay. Please check if I reduce the percentage. Is it okay? 40%. Okay. Okay. Right. So let us discuss the numericals. So we're having three expressions. Okay. So accordingly, we'll discuss the numericals now. Is it visible? Okay, I will zoom it. Please check. Okay, right. Okay. So now let us discuss the numericals. So first of all, read it. The periodic current through power semiconductor device in a switching circuit is given below. Yes, this is a periodic current they have shown. Okay, they have mentioned the periodic current is shown in the figure. Okay, given below. Next, a BJT with a device drop of 1.2 volts and MOSFET with on state resistance of 150 milliohm are considered for the application. Find the loss in both the devices. Okay, find the loss in both the devices, and they have given the current waveform. It is like this. This is a given data. This is periodic current. Time t is in microsecond. So linearly increasing, constant, linearly decreasing, constant, and this type of waveform, right? So this is a 10 ampere amplitude. Okay. So, yes, this is the current waveform they have given, and it is given that a BJT with a device drop means VT is given. For BJT it is a 1.2 volt, and a MOSFET with on state resistance means Ron is given 150 milliohm are considered for this application. Find the loss in both the devices. Yes, how to find the BJT power loss? Come on. How to find the BJT power loss? Just now I discussed. BJT power loss. VT into I average or IRMS? I average, right? VT into I average, right? And for MOSFET, it is a IRMS square into R, right? IRMS square into R. So we need to find it. So let me first of all find the average value of this current and RMS value of this current. Okay, so that we can find the power loss in a BJT and power loss in a MOSFET. Okay, so let me write first. Yes, on state resistance of MOSFET is given, that is a R on. For MOSFET, it is a 150 milliohm, 150 into 10 to the power minus 3 ohm. This is for MOSFET only. On state voltage drop given, that is a VT, is a 1.2 volt. This is for BJT. This is for BJT. So first of all, let us find I average and IRMS. How to find the I average? I average is equal to 1 by T. Yes, it is a area, na? 1 by T into area under the current I waveform. So it is a 1 by T into area of current I, right? So it is equal to 1 by T into, now you can check in the current we are having like, here it is a triangular, here it is a rectangular, and here it is again triangular shape. Okay, so can we find the area of this triangle, area of this triangle, and here area of the rectangle? Strictly speaking, area under this triangle and area under this triangle both are same only, because 0 to 5, and here it is 15 to 20, that is a 5 microsecond and 5 microseconds we are having. Okay, so simply you can find the area under this, multiply it with the 2, or you can find the area here, and again next the area under the rectangle. Okay, so first how to find the area under this? So it is a 1 by 2 into 5 micro, na? Right? So it is a 5 into 10 to the power minus 6 into what is the amplitude? It is a 10. Okay, into 10. So this is the area of this triangle, correct? 1 by 2 into 5, time is in microsecond, so it is 1 by 2 into 5 micro into 10. Next, how to find the area of this rectangle? It is 5 to 15 means this length is 10 microsecond. Okay, this is a 10 micro and this is a 10. Okay, so let me write it as plus 10 into 10 to the power minus 6 into 10. This is the area of the rectangle. Okay, and the third one is the area of this triangle again. It is the same, na? 1 by 2 into this length. Okay, so it is a 1 by 2 into 5 into 10 to the power minus 6 into 10. Let me, yes, comment here. This is your area of the triangle. First triangle. This is the second triangle. Area, right? And this one is rectangle. Is this clear? Okay, now we need to simplify it. So if you simplify it, we'll be getting it as, and what is the T? Yes, what is the T? T is from this point to this point, na? The total T you can check. T is this one. It is a 30 microsecond, na? 30 microsecond. So we need to replace this T with 30 microsecond. Okay, so I will write here. So it is equal to 1 by 30 into 10 to the power minus 6 into this term. Let me check this term. Into 10 to the power minus 6, right? It is 150, na? Into 10 to the power minus 6, correct? 100, this is 25, 20, 50, right? So it will be like 5, okay? 5 ampere. This is the I average, correct? Next, IRMS we need to find. IRMS. RMS value. How to find the RMS value? We need to find the RMS of this triangle. Okay, and here it is triangular function, and this is the rectangular function. Okay, so simply we can find the RMS. It is a, for triangular function, it is a square by 3, na? Right? A square by 3 into, this is 5 micro divided by 30 micro. Okay, a square by, a is 10, na? So 10 square divided by 3 into 5 micro divided by 30 micro. This is for first triangle. Similarly, for second triangle also we'll be getting the same. Okay. Next, for the rectangle, it is a 10 a square. So it is a 10 square. Okay. Into we're having the, this time is 5 to 15, na? So it is a 10 micro. 10 into 10 to the power minus 6 divided by total time period is 30 into 10 to the power minus 6. Plus again the same for the second triangle. 10 square divided by 3 into 5 into 10 to the power minus 6 divided by 30 into 10 to the power minus 6 to the power 1 by 2. Is this clear? Means whatever we have written, yes, whatever we have written for triangular function, expression for the RMS, okay, for rectangular function, expression for RMS, the same thing we have, yes, used here. Is this clear? No. Srivara. T is a 20. T is a your 30 here. This full is T we need to consider. This full is T we need to consider. Are you getting the point? Right? So this is your periodic time or the periodicity you can say. Right? So if you simplify it, please check what is the answer. So 10 to the power minus 6 cancel out. Minus 6 cancel out. Minus 6 cancel out, right? So it will be like 6.66, right? $6.67, right? It is a 6.67 ampere. This is your IRMS. Some participants are raising the hand. Okay. Right. Next, now can we find the power here? So power, on state power of BJT. On state power of BJT. For first, on state power loss in BJT. In BJT. Yes, P on is equal to I average into VT. Na? I average is 5 into what is the VT? VT is 1.2. Right? It is a 1.2 they have given. So it is into 1.2. So it will be equal to 6 watt. This is a P on. Correct? And what about in the MOSFET? On state power loss in MOSFET. P on is equal to I RMS square into R on. It is 6.667 square, right? Into R on. R on is 150 milliohm they have given, right? 150 milliohm. So into 150 milliohm. So if you check, it is equal to 6.67 watt, right? This is a P on. Is this correct? Yes, average is 6 watt and this is 6.67, right? Yes. Are you getting the point? So now you can check here. We are having at one side, we are having a BJT. At second side, we are having the MOSFET. Okay. So in the MOSFET, the power loss is somewhat little bit higher than that of the BJT. BJT power loss is 6 watt. And here on state power loss of the MOSFET is 6.67 watt. So keep it in mind. MOSFET power loss is always high. Okay. Somewhat greater than that of your BJT power loss. One more thing. These values, okay, these values are not randomly given. Means it is like 1.2 volt and this 150 milliohm. These are not the random values. These values are having the relation that when for a particular current, if BJT is causing a voltage drop of 1.2 volt, then the MOSFET is offering a resistance of 150 milliohm. Okay, these are the standard values. These are the standard values. Okay, so power loss for the same current, the power loss in the MOSFET is a greater than that of the power loss in a BJT. Okay, please note it, right? Note it. Next. Yeah, let us discuss the next example. A thyristor used in application carrying half sinusoidal current of 100 ampere peak value as given in figure. Okay, peak value, here it should be value, right? Okay. As given in figure, the thyristor may be modeled during conduction to have a constant voltage drop of 1.1 volt and a dynamic resistance of 8 milliohm. Evaluate average conduction loss in the device for this application. Okay, our task is to find the conduction loss. Okay, for this application. Yes, it is given that current waveform they have given. This is a current waveform. This is omega t 0. Just a minute. It is not responding. Okay, so this current they have given, it is a 100 ampere peak value. 0 pi, 2 pi, and here it is 3 pi, right? This is the current flowing through the thyristor. Thyristor on state voltage drop is 1.1 volt and the resistance is given, it is a 8 milliohm. Okay, our task is to find the power loss, conduction loss, that is nothing but the on state power loss. Okay, on state power loss. So it is like a combination of voltage source and a resistor. So what is the on state power loss? It is a I square RMS into R on plus I average into VT. Yes or no? Right? So first of all, we need to find the average value of the current and RMS value of the current. Right? So how to find the average and RMS value of current for this type of waveform? It is like a half rectified, okay, waveform we're having, half wave rectified. So let me write, VT is given, it is a 1.1 volt and resistance, on state resistance is equal to 8 into 10 to the power minus 3 ohm. These are the given things. I average, let us find I average. So how to find the average value? Yes, here we cannot find directly the area. Yes or no, it is a sinusoidal we are having. So how to find the average value? So we need to use the basic expression, right? Average is equal to 1 by that time t. Now instead of time t, we are having the angle here. Na? Omega t means what angle? Omega is in radian per second and t is in second. So it is radian per second into second. Second will get cancelled out. So it is a radian only. Omega t is a angle. Okay, omega t is angle. Now can we write the expression for this waveform? It is a sinusoidal, na? So it is a Im into sine of omega t. Yes or no? Right? Im into sine of omega t. You can check when omega t is 0, that is this omega t is 0, sine 0 is 0, so that's why it is 0. As omega t increases, sine value increases, right? So this current I is also increasing. At pi by 2, at omega t is equal to pi by 2, you can check sine pi by 2. Sine pi by 2 is 1, so it is Im into 1. that is Im. So value is Im. Now this indicates your Im. Okay, this indicates your Im. So let me indicate here. Yes, this is a Im actually. Im, right? So can we say that Im is 100, right? Im is equal to 100 ampere. Im is equal to 100 ampere. Next, after pi by 2, what is happening? Again, as omega t increases, sine value goes on decreasing. So current I also decreases. At omega t is equal to pi, sine pi is 0. So that's why Im into 0 will be again 0, right? So this expression is valid only from 0 to pi, right? Please be careful. This expression is valid only during 0 to pi, right? Next, now our task is to find the average value. So what is the average value? How to write it? Okay. First of all, we need to integrate it and divide it with a periodic time. Now instead of time here we are having the angle. So we need to write it as 1 by 2 pi. What is the periodic angle here? 0 to 2 pi. Na? Whatever the waveform we are having 0 to 2 pi, the same is repeating from 2 pi to 4 pi. Same will repeat from 4 pi to 6 pi. So therefore periodic angle is 1 by 2 pi. Periodic angle is 1 by 2 pi, right? Next, we need to take the integration over 0 to 2 pi. Integration over 0 to 2 pi, but between 0 to 2 pi, we're having the two sub intervals. One is a 0 to pi, second one is a pi to 2 pi. Between pi to 2 pi, what is the current? It is a 0, right? So effective interval will be only 0 to pi. Yes or no? Effective interval will be only 0 to pi, right? So let me write it as 0 to pi only. Because from pi to 2 pi it is 0, no? So integration of that 0 will be 0, right? So it is 1 by 2 pi integration from 0 to pi. What is the value? It is a Im into sine of omega t into d omega t, right? So this is the expression for the average value. Next, we can write it as, we need to simplify it. Im is a constant, so take it outside. Im by 2 pi. What is the integration of sine of omega t? It is a minus cos of omega t. Minus cos of omega t 0 to pi, right? So if you put the limit, it is like a Im by 2 pi into minus cos of pi plus cos of 0. What is cos pi? Cos pi is minus 1, na? So it is equal to Im by 2 pi into minus of minus 1, okay, plus cos 0 is 1. So minus of minus 1 is plus 1 and this plus 1. So it will be like 2. Okay. So these two will get cancelled out. So therefore it is equal to Im by pi only. What is Im? Im is, we know, na, it is 100. Im we know it is 100. So can we write it as 100 by pi? So let me write it as 100 divided by pi. Right. So what is 100 by pi? If you check, it is 31.83 ampere. This is your I average. I average, right? Similarly, we need to find IRMS. We need to find the IRMS, right? So IRMS is equal to 1 by 2 pi square root of mean of squared value. Okay. So 1 by 2 pi integration from 0 to pi. Now we need to square the instantaneous values. So instead of Im sin omega t, it should be Im square sin square of omega t into d omega t to the power 1 by 2. Square root of mean of squared values. Okay. Mean of the squared values we are taking. So it is equal to, we can write, let me take this Im square outside of this square root. Okay. So it is like Im divided by root 2 pi. This root 2 pi also, this divided by 2 pi also I am taking outside the square root. So that's why it is the root 2 pi. Into, we can write it as integration from 0 to pi. Sin square of omega t can be replaced with 1 minus cos of 2 omega t by 2. We cannot find the integration of sin square of omega t directly. So that's why we need to replace sin square of theta with 1 minus cos 2 theta by 2. Okay. To the power 1 by 2. Next, it is equal to Im upon, I am taking this divided by 2 also outside. So that root 2, right? And this root 2 will become 2. So 2 root pi into, we can write it as a integration over 0 to pi. Let me write it as 1 minus cos of 2 omega t. Okay. Into d omega t. to the power 1 by 2. So we can write it as Im upon 2 root pi into, it is like a omega t, right? Limit 0 to pi, okay? Minus integration of cos of 2 omega t. It is a sine of 2 omega t divided by 2, limit 0 to pi to the power 1 by 2, right? We can simplify it, is equal to Im upon 2 root pi into, it is like pi minus 0, okay, minus, you can check, put the limit, sine of 2 pi, sine 2 pi is sine 360, na? Sine 360 is 0, right? And put the lower limit, sine of 2 into 0, sine of 2 into 0 is again 0. So it will be like 0 minus 0 to the power 1 by 2, right? So this root to this root pi will get cancelled out. The only thing is Im by 2. What is Im? 100 divided by 2. So it is a 50 ampere. We are getting IRMS is equal to 50 ampere, right? IRMS is equal to 50 ampere, correct? Now, can we find the power loss? This is very simple now. It is a Vt into I average. Therefore, power loss is equal to Vt into I average plus I RMS square into Ron. So we can put the value, Vt is 1.1 into I average 31.83, right? Plus I RMS 50 square into Ron. Ron is 8 milliohm. So it is 8 into 10 to the power minus 3. So if we simplify it, we'll be getting 55 watt, right? 55 watt. This is a power loss. That is an on-state power loss. Is this clear? Correct? Good. Please check. Someone has written 75 watt. No, 55 is the correct answer. Please check. Okay. Next. Yes. Let us discuss this numerical. A diode, its number is given 20ETS08. Okay. Doesn't matter. That information we are not required here. A diode is a 20 ampere 800 volt rectifier diode. Okay. So diode current rating and voltage rating is given. The meaning is here. Please be careful. What the current rating and voltage rating of the diode indicates? The current rating of the diode is nothing but the maximum current with which the diode can withstand. Okay, means when the diode is in an on state, then how much maximum current the diode can carry is equal to your 20 ampere is given. And what that 800 volt indicates? The 800 volt indicates when diode is in an off state. When diode is in an off state, then how much maximum voltage with which the diode can withstand. Okay, so that voltage is 800 volt. I am saying for voltage rating, I am using the word blocking. Diode is in an off state. I am saying diode is in an off state. And for current rating, I am using the word, it is a diode is in an on state. So please keep it in mind. Current rating is associated with your on state of the diode. Voltage rating is associated with your off state of a diode. Are you getting the point? Because when diode is in an on state, then what is the voltage? It is a very small number. Whether that voltage will be 800 volt? No. When the diode is in an on state, the voltage across diode will be very low. That is around 0.7 volt or 1 volt or 1.5 volt, etc. Right? It is an on state voltage drop actually. Are you getting the point? Right? So 800 volt indicates the maximum voltage the diode can block. I am saying diode can block when it is in an off state. And 20 ampere is nothing but the maximum current the diode can carry. Okay. without self damage. Okay, when it is in a off, when it is in a on state, when it is in a on state. Please try to understand. Yes, yes, all are the power devices only, Vedant. Right. So next, so let us read the question. A diode is a 20 ampere 800 volt rectifier diode. It has a voltage drop of 0.8 volt at 2 ampere and a 1.2 volt at 30 ampere. 1.2 volt at 30 ampere. If this diode is carrying a 30 ampere current, okay, of half sine wave, please, one word is missing here. If this diode is carrying a, yes, peak 30 ampere of half sine wave. Okay, 30 ampere is a peak value. Actually 30 ampere is a peak value of that half sine wave. Okay, that word is missing in the booklet, please correct it. If this diode is carrying a 30 ampere peak, okay, of half sine wave of current, then the conduction loss in the device will be, okay, conduction loss in the device will be, that we need to find. Okay, so first of all, let us note the data. This diode rating is not required for us, right? So diode is represented during its on state, conduction loss they have asked na. So during the on state, how the diode is represented? Diode is represented with a on state voltage drop and in series with the resistor. Yes or no? On state voltage drop and in series with the on state resistance. Okay, so let me show here. The diode is represented like this: on state voltage drop and a resistance. So R on, and this is a VT. These are the diode terminals. Okay, means when diode is in a on state, when diode is in a on state, so it is like this. This is a diode we are having, A and B. When this diode is in a conduction mode, when this diode is in a conduction mode, okay, so current will be flowing through the diode. At that time, this full structure can be replaced with this equivalent circuit, this equivalent model. Are you getting the point? Okay, so when diode is in a conduction mode, at that time we can replace this symbol with this equivalent model, with this equivalent model, right? Now it is given that for a 2 ampere current, let me first consider the current here is I. Let me consider current is a I. Okay, for a 2 ampere current, the voltage drop is 0.8 volt. Be careful, this voltage drop of 0.8 volt is nothing but this voltage drop. This voltage drop V I am saying. The voltage drop given 0.8 volt. It is not that your VT. The voltage drop is this V is given. This V is given. Because voltage drop across the diode na, and across diode is connected between A and B terminals. So here it has a voltage drop of 0.8 volt. The meaning is the voltage across A and B terminals is equal to 0.8 volt. When the current is 2 ampere flowing. When the current of 2 ampere is flowing. Similarly, and 1.2 volt, that voltage drop is 1.2 volt at a 30 ampere. Means when a current of 30 ampere is flowing na, at that time the voltage drop across the diode, that is the voltage across AB terminals, okay, is equal to V, which is equal to how much? 1.2 volt. These two conditions they have given. Are you getting the point, right? And if this diode is carrying a 30 ampere of half sine wave of current, then conduction loss in the device will be. So my question is, here we are having the diode equivalent model is R on in series with the VT. So the conduction loss will be I RMS square into R on, right, plus I average into VT. Yes or no, right? So we need to find first I average and I RMS. After that, we need to find, yes, from these two data, right? This data they have given 0.8 volt at 2 ampere and 1.2 volt at 30 ampere. From this data, we need to find R on value and VT value. They have not given the R on value and VT value. Please be careful, right? We need to find it. And they have given the data to find the R on and VT value, right? So let me first write. Yes. Let us first find the R on and the VT value, then we'll proceed. Okay. So let me write for, yes, diode for diode. Okay. Yes. can we write V is equal to this voltage V? Simply we need to apply the KVL here. If we apply KVL here, what we will be getting? It is a -2 plus, that is a plus V, minus I into R1 minus VT is equal to 0. Yes or no? So can we write for a diode during on state, if we are having this is the model of the diode, then can we write plus V minus I into R1 minus VT is equal to 0, right? So let me write. For a diode, we can write plus V minus I into R1 minus Vt is equal to 0. So therefore, it indicates, therefore, V is equal to I into R1 plus Vt. Yes or no? Correct? So V is equal to I into R1 plus Vt. Now, they have given the data like for V is equal to 0.8 volt and current of 2 ampere. Okay. And 1.2 volt V, the current of 30 ampere. So we can write from given data. From given data. Yes, we can write V is equal to 0.8. Okay. Is equal to current is how much? The current is your 2 ampere, right? So 2 into R1 plus Vt. This is your equation number 1. Similarly, they have given one more thing. V is equal to 1.2 volt and current is 30 ampere. Okay, so 1.2 volt and current is 30 ampere. Na? So current I should be 30 here into R1 plus Vt plus Vt. This is your equation number 2. This equation I have written from, yes, for V is equal to 0.8. Okay. Yes, and I is equal to how much? It is a 2 ampere. And second one, V is equal to, it is given 1.2 volt and current is given 30 ampere. So accordingly, I have written 2 equations. Now we need to simplify these 2 equations, right? You can simplify either by using direct calculator or manually also you can simplify. How to simplify? If I subtract equation 1 from equation 2, it is like minus here, minus here, minus here. So this Vt will get cancelled out. 1.2 minus 0.8, so it is equal to 0.4 is equal to 28 into R1. So from this, can we find R1? Therefore, R1 is equal to 0.4 divided by 28. So if you check, it is yes 0.01428. 0.01428. Okay, ohm. This is the R1. We can put this R1 in either equation 1 or 2 to get Vt. Okay, put R1 in equation 1. So from this we can get Vt. Na? So therefore Vt is equal to, we can write it as 0.8 minus 2 into, it is 0.7714, right? 0.77144. Okay, volt. This is the Vt. Now what is the power loss? I RMS square into R1 plus I average into Vt. So we need to find I RMS and I average also. And which type of current is flowing they have given? Yes, if this diode is carrying a 30 ampere peak, okay, peak 30 ampere of half sine wave of current. So half sine wave current we are having, that current is flowing through the diode. Okay, so current is like this. Current which is flowing through the diode is like this. Okay, pi, 2 pi, 3 pi. What is the peak value they have given? This is a 30 ampere. This peak value is a 30 ampere, right? Now can we find the average value? We have calculated in the previous example itself. So average, what will be? I average is equal to, it is a Im by, you can check, Im by pi, right? And RMS is Im by 2. This is RMS. So directly I can write, yes, I average is equal to Im by pi, which is equal to 30 divided by pi. So you can check 30 by pi means 9.55 ampere. This is I average. Okay, I RMS IM upon 2. So it is equal to 30 by 2. No? So it is a 15 ampere. Okay, this is the IRMS. Next, now can we find the power loss? Yes. So please check for power loss. Power loss or on state conduction loss, you can say, right? So it is a VT into I average plus I RMS square into R on, correct? So you can put the value. VT is we have calculated 0.77144 into I average, that is a 9.55 plus 15 square into R on. R on is 0.01428. Right? So if we simplify it, we'll be getting it as, yes, 10.58, right? That this is a P loss. Correct? Is this clear to all? Right. Next. So these are some of the numericals related to the power loss, okay, during the on state, or you can say the conduction loss. Now let us discuss some numericals related to the switching loss. Okay, switching loss, either you can say the energy loss during the switching or the power loss during the switching. This type of numericals also they have asked, right? So let us discuss one by one. This question is from GATE 2016. The voltage Vs across switching loss, first of all let me clear. Conduction loss means what? When the device is in a on state, okay, then whatever the power loss is there, that will be your conduction loss. And switching loss means what? The power loss or the energy loss during the transition period, that is nothing but your switching loss. Is this clear? One word is the conduction loss, second one is the switching loss. Switching loss is related to your transition period, okay, and the conduction loss is like your on state power loss. Okay, next, generally the off state power loss is very small. Generally the off state power loss is very small, so that's why generally we neglect it. Okay, so that's why they will not ask the numericals related to the off state power loss, because when the device is in a off state, how much current is flowing through the device? It is hardly the microampere, na? So what is the power loss? That will be negligible power loss. Okay, but when device is in a on state, the power loss will be we can take the we can consider that due to the high on state resistance as well as that voltage drop, right? That will be getting some power loss, right? So let us discuss this numerical. The voltage Vs across and current Is through a semiconductor switch during a turn on transition are shown in figure. Okay, the energy dissipated during the turn on transition in millijoule is, okay, so they have given and they have commented that through a semiconductor switch during the turn on transition, they have directly given that it is a turn on transition. You can check whether it is a turn on transition or not. Okay, so you can check before this instant and after this instant. This time they have given it is a T1 and here it is T2. Is this visible? Okay, okay, okay. Yes, no, yes, no. Okay. So let me put it 50%. Please check now. Okay, yes. Right. So now this question is from GATE 2016, and it is given that they said that it is a turn on transition. Okay, we'll discuss it why it is a turn on transition. So here you can check before this instant. Yes, means before this T1. Okay, means before this instant, if you check, yes, here it is like a voltage is high voltage, 600 volt, and current is 0. So voltage is high and current is 0 means, can we say that the switch is in a off state? Yes or no? Right? So before this instant, the voltage is high, means you can check before this instant, means voltage before this instant. Okay, so before this T1 instant, the voltage is high, current is 0. The meaning is switch is in a off state. Here the switch is in a off state. After this instant, if you check, voltage is 0. After this instant means after this. So here it is after this instant. Voltage is 0, current is 100 ampere. So current 100 means current is high. Voltage 0 means voltage is low. Right? So here can we say that the switch is in a on state? When switch is in a on state, voltage is very small. Ideally speaking, it should be 0. But in practical cases, there will be some voltage drop taking place. Right? So voltage is less, current is more, means switch is on. Before this instant, voltage is more, current is 0, means switch is in an off state. So between these 2 points, that is T1 plus T2, na, this instant is, this interval is T1, this interval is T2. Okay, so can we say that? Yes, 55. So this interval is T1, this interval is T2. So can we say that yes, T1 plus T2, this interval indicates your turn on transition because it is off to the on. Na? So that's why it is a turn on transition, right? So this full indicates turn on transition. Turn on transition. Is this clear? This is a turn on transition. Now our task is to find the energy dissipated during the turn on transition in millijoules. They have asked me. Okay. So how to find the energy dissipated? Whatever the expression we derived in the yesterday's session, it is like 1/6 into V into I na, into that TR and TF in terms of TR and TF. But that was valid only when corresponding to that respective transition, one is linearly decreasing, second one is linearly increasing. But in this case, you can check during T1, what is happening? Voltage is constant. During T1 means during this instant. This is also T1 na? During T1, voltage is constant. This is a Vs. This is a Is. Okay, this is Is. So during T1, voltage is constant, current is increasing. So whatever the expression we derived in the yesterday's session, that expression we cannot use here. Are you getting the point? Right? Second, during T2, you can check voltage is decreasing, current is a constant. Na? During T2 means during this interval, voltage decreasing linearly and current is a constant. Okay. So one is a constant, second one is a decreasing linearly, right? So that expression we cannot use here blindly. Okay, so now let us find how to find the energy dissipation in this case. Okay, so we know energy means what? Integration of power is nothing but the energy. Yes or no, right? So let us first find the energy dissipation during T1, energy dissipated during the T1 interval, right? So let me write. Yes, I'm writing here. Yes. Energy dissipation or energy dissipated during T1. Okay, during T1. So let me write it as ET1. Let me write it as ET1 is equal to what? ET1 is equal to energy, nothing but integration of power. Okay, so it is equal to Vs into Is into dt. That's it. Vs into Is is nothing but your power. Integration of that power is nothing but the energy. So integration of Vs Is dt is nothing but your energy dissipated during T1. Now during T1, what is the Vs? Vs is a constant na? During T1 600 volt, no problem. But what is the Is? Whether Is is a constant during T1, you can check Is is a linearly increasing. So we need to write, yes, we need to write the expression for the IS. Okay. But while if you write the expression for IS and if you simplify, it will take a time. It will be a time consuming. Okay. So how to simplify it? Let us discuss. So ET1, therefore ET1 is equal to what? Vs is a constant now. So I have taken it outside. Integration of IS into dt. IS into dt. What this integration of IS dt indicates? Integration of IS dt, what this indicates? This is during T1. So that's why let me write it as 0 to T1. So it should be 0 to T1 only. Integration of IS means, can we say that area of the IS over the interval T1 only? Okay, so this is the area of IS, right? Area of IS. So is equal to, therefore ET1 is equal to Vs into, what is the area under this IS? IS means this one. Are you getting the point? Or let me draw the IS separately here so that you will understand. During T1 IS I am drawing. This is your IS. Here, from here the T1 starts. So here it is T1 actually. This full interval is T1. Okay. IS is like this, increasing. Okay. So you can check here. From 0 till this infinity. What this point indicates? This point is nothing but this is 100 plus this 50. So can we say that this point is 150, right? So this is equal to 150 ampere. 150 ampere. Okay. So can we say that during 0 to T1, if this is T1 and if I am saying that this is the 0, then can we say that this is equal to T1? So 0 to T1 means this interval. So corresponding to this, we are having IS is nothing but this triangle. So area under the triangle is equal to what? 1 by 2 into T1 into this 150, right? So this is equal to 1 by 2 into T1, okay, into 150. Is this clear? This is nothing but area of IS. Let me show. This is your area of IS, right? So now we can put the values. So therefore ET1 is equal to Vs is 600 na, into, it is like a 1 by 2 into T1 is how much? 1 microsecond. 1 into 10 to the power minus 6 into 150. So you can check, it is equal to yes 0.045, right? Joules na. So this is the ET1. Energy dissipated during T1. It is a 0.045 joules. Correct? Next, similarly, can we find for T2? Energy dissipated during T2. Next one, energy dissipated during T2. T2. Correct? So ET2, let me write it as ET2 is equal to, again, integration. It is like a 0 to T2 Vs into Is into dt. Now you can check here over the T2, over the time period T2, Is is constant 100 ampere and Vs is decreasing. So we can take Is outside. Is is constant, so I am taking it outside. So it is equal to ET2 is equal to Is into integration over 0 to T2 Vs into dt. What this indicates? Integration of Vs is nothing but what? It is the area under Vs, na? Area under Vs. Yes or no? Right? So how to find the area under this curve Vs? You can check over T2 we are having. Over T2 means from this point till this point. Vs is a triangular, na? So area of the triangle we need to consider. It is a 1 by 2 into T2 into this 600, right? So it is, therefore ET2 is equal to Is. Is is constant, so it is 100 into 1 by 2 into 600 into T2. T2 is, it is a 1 microsecond, right? So it is a 1 into 10 to the power minus 6, correct? So you can check, it is a, yeah, I think 0.03 na. right? 0.03 joules. This is the ET2. So therefore, energy dissipated. Therefore, total energy dissipated. Total energy dissipated during turn on transition. Turn on transition. Yes. Is equal to ET1 plus ET2. So you can check it is a 75 millijoules. Okay, 75 millijoules. Right? So they have asked the answer in millijoules. Huh? So that's why we need to write here only 75. Right? Only 75. If you write 0.075, you will not get marks. Is this clear? And this is a numerical answer type question. Okay. So here you need to put the number. You need to put the number, right? NAT type question. Generally, these type of questions, there will not be these type of questions will not be having the negative marking. Okay. So this is about the one numerical. Let us take a break here. It's a 7. We start at 7:15. Okay, 7:15. 15-minute break will be there. Yes. Raj. Duration for ET2 will be from T to T2. No. Please check duration of T2. If this is T2, if this is T2, and if I consider this as a 0, then this will be your T2, na? Are you getting the point? If this is a T2, this difference is T2, then I am considering this as a 0 and this is a T2 because we are considering only this interval, na? So that's why I have written 0 to T2, right? Please give break for 20. Okay. Okay. We'll take a break of 20 minutes, right? Yeah. Okay. Let's discuss next example. Power electronic switch during its turn on process has the following data, right? This data they have given: anode voltage 600 0 and anode current 0 100. So it is given that during turn on process, okay, during turn on process, anode voltage is actually changing from 600 volt to 0 volt, and anode current is changing from 0 ampere to the 100 ampere. This is the meaning. Okay, during turn on time of 5 microsecond, the anode current and anode voltage vary linearly, right? Means anode voltage is decreasing linearly and anode current is increasing linearly, right? If triggering frequency is 100 hertz, this is a triggering frequency. Find the average power loss in the switch. Okay, our task is to find the average power loss. So before solving the numerical, let us discuss what this 100 hertz indicates. Okay, because yesterday someone asked the question regarding the triggering frequency. Okay, so if triggering frequency is 100 hertz, the meaning is in 1 second I am turning on the switch, okay, and turning off the switch 100 times. Okay, I am turning on the switch 100 times, and definitely if I am turning on the switch 100 times, means somewhere it should be turned off. Yes or no? Somewhere it should be turned off. Before turning it on, definitely switch should be turned off. Okay, so here please try to understand the meaning. Let me consider this is a time 0. Okay, 100 hertz means in 1 second it is a 100 times. Okay, switch is turned on. In 1 second 100 times the switch is turned on. For example, suppose before this instant the switch is in a off state. Switch is in a off state. Before this instant switch is in a off state. So what is the voltage across switch? It is a 600 volt, high voltage na, and current flowing through the switch is 0 ampere. Current flowing through the switch is 0 ampere. So let me indicate here, right? Current is 0 ampere, voltage is 600 volt. So this is the V and I. This indicates a 600 volt and the current is 0 ampere. During turn on process, means what? This is during the turn on transition. Voltage is decreasing from 600 to 0. Voltage is decreasing from 600 to 0, and it is, they have given the anode current and anode voltage vary linearly na? So voltage is decreasing linearly from 600 to 0, and current is increasing linearly. Current is increasing linearly from 0 to 100 ampere. So it is a 0 to 100 ampere. So after this instant, can we say that the switch is in a on state? Switch is in a on state. Okay, so after this the current is constant and voltage will be your 0 volt. Voltage will be constant, that is a 0 volt. Now this is a one turn on. This is a one turn on. Let me indicate this time as T on. Right? Let me indicate this as a T on, because they have showed the turn on process na, and turn on time they have given 5 micro. So let me indicate it as a T on. Now as the triggering frequency is 100 hertz, triggering frequency is 100 hertz, means in 1 second the switch is turned on 100 times. Switch is turned on 100 times. So here can we find the time interval between two turn on instants of the switch, right? Means if I am turning on the switch at this instant, after how much time interval the next turn on instant will start? You can check, it is a 1 by 100. 1 by 100 means what? If the frequency is 100 hertz, so time taken to complete one cycle is 1 by 100. Yes or no? Right? So if you check 1 by 100 means it is a 0.01 second. So after 0.01 second, means suppose this time, let me indicate this time as 0.01 second. Okay, means actually between these two instants, this time is 0.01. Let me show it as a, yes, right? So this time is actually 0.01 second. This is a 0.01 second. Means once we turned on, after that the next turn on will start at, yes, after 0.01 second. Is this clear? So after that again the same waveform will repeat. Means if the turn on will start from this instant, means the same waveform will repeat from this point again. Okay, means this is switch is turned on here. So before this instant, there should be somewhere the before this instant switch should be turned off somewhere, na? Right? Are you getting the point? Means before this instant, in order to turn on again, the switch should be turned off somewhere. Okay, and they have not mentioned anything regarding the turn off. So simply we need to assume that it has turned off before this instant, and after that again the same cycle will be like this. We'll be getting, it will be decreasing here from 600 to 0, and current is increasing from 0 to 100 ampere. Okay, so this is 0.01. After next 0.01 interval, again the next turn on time will start, right? So like this, in 1 second we are having 100 times, okay, switch is turned on, 100 times the switch is turned on. Is this clear? This is nothing but your triggering frequency. This is the triggering frequency, right? Now our task is to find, yes, average power loss in the switch. Power loss in the switch. Okay, we know now power loss in the switch. Yesterday we discussed, it is equal to triggering frequency into energy loss, right? Triggering frequency into energy loss. Frequency we know 100 hertz. The only thing is we need to find the energy loss. We need to find the energy loss. So let me write here, energy loss during turn on. Energy loss during turn on time. Now you can check during the turn on time is, this is your turn on time. During this interval, what we are having, the voltage is decreasing linearly and current is increasing linearly. So for this type of waveform, whether yesterday we have written the expression for energy loss, yes, we have written. What was that expression? It is like a 1/6 into voltage into current into what? It is a T on. The time interval is T on. The same expression we wrote yesterday. You can check here. Yes. We have written now 1/6 into V into I into TR, right? This is for turn on TR. And if we want for a second interval, it is again 1/6 into V into I into TF. Okay. The only thing is the time will be changing. The remaining terms will be same, right? So here, yeah, 1/6 into V into I into T on. Okay. So it is equal to 1/6 into what is V? It is a 600 now. Current is 100. And what is the time they have given? It is a 5 microsecond. So it is a 5 into 10 to the power minus 6. So you can check it is equal to 0.05, right? 0.05 joules. 0.05 joules. This is the energy loss during the turn on period. Okay, turn on time. So what is the power loss? So therefore power loss is equal to energy loss into frequency, right? Into switching frequency. Switching frequency, right? You can check here 0.05 into switching frequency is 100 hertz, right? So it will be equal to 5 watts. Is this clear? So this is the power loss, which is equal to 5 watt, right? So either you can simply, yes, memorize this expression and you can solve it, or what you need to do, we need to write the expression for this waveform, expression for this waveform, and then we need to simplify that integration. Okay. Next, let us discuss the next example. Okay. Shall I repeat it again? Yes. Okay. Yeah. Please check. Yes. Let us first read the data. This question is from GATE 2005 examination. Not this one. I'm sorry. Yeah, this question actually. I am repeating this. The power electronic switch during turn on process has the following data. Anode voltage 600 to 0 volt. It is given that anode voltage is decreasing, right? They are yes given that very linearly, na, means anode voltage is decreasing linearly from 600 volt to the 0 volt. We know na, during turn on, voltage across switch decreases, current flowing through the switch increases. Anode current increases linearly from 0 ampere to the 100 ampere. During turn on time of 5 microsecond, the anode current and anode voltage vary linearly, right? Turn on time is given, that is 5 microsecond. Means during the 5 microsecond, yes, this voltage is decreasing linearly from 600 to 0. Current is increasing linearly from 0 to 100. If triggering frequency is 100 hertz, find the average power loss in the switch. Okay, so first we discussed about triggering frequency. Triggering frequency is 100 hertz means what? The switch is turned on 100 times, okay, in 1 second, right? So if the switch is turned on 100 times in 1 second, okay, so suppose at this instant I am turning on the switch. So after how much time instant, or after how much time the next turn on time will start? That will be after 0.01 second. You can check 1 by 100, that is a 0.01. Okay, so after 0.01 again we will be having next turn on time. Okay, so during turn on you can check the voltage is varying, decreasing linearly, current is increasing linearly, right? And this time is we are having, it is a 5 microsecond, 5 into 10 to the power minus 6 second. Now for this, yes, first of all we have calculated the energy loss, and after that the power loss. Yesterday we discussed if during this time interval, if we are having the voltage is linearly decreasing and current is linearly increasing, or voltage is linearly increasing and current is linearly decreasing, okay, we are having the expression like 1 by 6 into this voltage, initial voltage, into this initial current, or you can say the final current, okay, into that time. Okay, so we are having, it is 1 by 6 into this voltage 600, this current is 100 na, this current they have given, it is 100 ampere, right? You can check here, this is 100 ampere. So it is 600 into 100 into 5 into 10 to the power minus 6. This time is 5 into 10 to the power minus 6, right? So like this, we have calculated the energy dissipation, and from energy we can calculate the power. Okay, frequency into energy is nothing but your power, because power is nothing but energy divided by time, na? And that 1 by time is nothing but your frequency. So that's why it is a 5. Clear? Right? Yeah, for separate graph for I and V, it will be okay. V, this is time t. Suppose after this instant, before this instant switch is off, so after this instant voltage is decreasing na? So this is a your T on, this is 600 volt, this is a graph for voltage, and similarly we can draw the graph for current also. This is 100 ampere, correct? This is also T1, right? Similarly, after 0.01 second, again it will repeat the same plot. No, they have not mentioned anything about the turn off transition, right? They have mentioned only about the turn on transition. So we need to consider only turn on. They have not given anything about the turn off transition. Okay, so here that's why we cannot comment anything regarding the turn off transition. Okay, the only thing is turn on transition we need to concentrate. Correct? Okay, next. Yeah, let us discuss this question. This question is from GATE 2005 examination. Let me reduce this percentage. Yeah. Is it visible? Right. We'll discuss all your doubts after the session. Okay. Okay. We'll discuss it If the turn off transition is given after the session, we'll discuss, right? Next. So let us discuss this question. This question is from GATE 2005. The figure shows the voltage across a power semiconductor device and the current through the device during a switching transitions. Is the transition a turn on transition or a turn off transition? This is the first question. Is the transition is a turn on transition or a turn off transition? What is the energy lost during the transition? Okay, means we need to find the energy lost during the transition, and also the which transition is this one, whether it is a turn on or a turn off. Yes, can anyone? Whether it is a turn on transition or turn off transition? Turn on, right? Turn on transition. Okay, good. Correct. Why it is a turn on transition? You can check here. Transition is between T1 and T2. Okay, between this is a T1, this is a T2 we are having. Okay, this T1 plus T2, it indicates your transition. Okay, transition time we can say. So before this you can check, and after this you can check the voltage and current values. Before this, what is the voltage value? Before this instant, the voltage is high, na, current is 0. The dotted one is a current, and this solid line is a voltage. So before this instant, the voltage is high. This is a V and I. Okay, the voltage is a high and current is a 0. Current 0, voltage high. The meaning is switch is in an off state. So here I am writing switch is in an off state. After this instant, you can check. After this instant, right? Means after this, voltage is 0, na? Current is, yes, it is a constant value. That is a finite value. That is a I. So current is a finite value. Voltage is a 0. Means switch is in the on state. So initially switch was in off state. At the end of this transition period, the switch is in the on state. So here the transition is turn on transition only, right? So it is a turn on transition. Turn on transition, right? Next, so this is a turn on transition. Now our task is to find the energy dissipated. Okay, energy dissipated or the energy lost. So in this transition, we are having the two intervals. One is a T1, second one is a T2. So let us first find the energy lost during T1. Energy lost during T1. During T1, okay, T1. Let me write it as ET1. ET1 is equal to energy, nothing but integration of power. So integration of V into I into dt. Okay. So it is equal to, now you can check during T1 what is V. V is a constant now. So I can take it outside. So it is a V into integration of current I into dt. And the interval you can check, right? 0 to T1. Okay. 0 to T1. So what is this integration of current I indicates? Integration of current I is nothing but area under the current I, na? Area of the curve, right? Area under the current I. So during T1, how is the current I? You can check during T1, current I waveform, it is like a triangle we are having. Okay, so what is the area under the triangle? It is equal to V into, let me write it as 1/2 into, this is a T1, na? Yes, into this current value is capital I. So it is a capital I. So it is equal to 1/2 into V into I into T1. This is your ET1. Right? Similarly, we can find for T2, energy lost during T2. Energy lost during T2. During T2. Let me write it as ET2. ET2. Okay. So ET2 is again integration over 0 to T2. Right? Because this interval is T2 na. So I am considering this as a 0 now. Okay, 0 second. And this as I am considering it as a T2. So 0 to T2. Yes, during 0 to T2, this is small T2, V into I into dt. So you can check here. During 0 to T2 means during T2 interval, what is the current? Current is a constant, voltage is decreasing. Okay, So current is constant, so we can take it outside. So it is a current I, integration over 0 to T2 V into dt. What this integration of voltage indicates? It is a area, na? Area of voltage. So you can check voltage here during T2 voltage we are having, it is a triangle, na? Right? So area of this triangle, it is a 1/2 into T2 into V. So let me write it as I into 1/2 into T2 into V. So after simplification, it is like 1/2 into V into I into T2. This is ET2. So what is total energy? So therefore, total energy lost is equal to ET1 plus ET2, right? So again, we can write it as 1/2 into V into I into T1 plus T2. Yes or no? This is your total energy lost. So you can check the options. VI by 2 into T1 plus T2, right? VI by 2 into T1 plus T2 and turn on. Option A is the correct option, right? Okay, next. Kushal, direct formula of 1 VI by 6, why not used? Because that formula is valid only when, yes, it is like this type of condition. During the same time interval, one is increasing, second one is decreasing, then that formula is valid. But here in this case, you can check during this interval, we are having two sub intervals T1 and T2. During T1, voltage is constant, current is increasing, na? So whether can I use that expression here? No. During T2, current is constant, voltage is changing. So can I use one is constant, second one is changing, right? So we cannot use that 1/6 into V into I formula here. Is this clear? That formula is valid only when one is increasing, second one is decreasing during the same time interval. I hope it is clear, right? Okay. Okay. Next. Yeah, next let us discuss this numerical. A power switching device is ideal in conduction and blocking. Okay, power switching device is ideal in conduction and blocking. Okay, conduction and blocking means during on state and during the blocking means off state. Okay, so it is given that ideal 0 volt drop and 0 ampere current. The meaning is we are having the power switching device. They have given during the conduction state, the voltage drop is 0. And during the blocking state means off state, the current flowing through the device is 0 ampere. Okay, right? Means it is just like your ideal switch. It is used in a circuit. It is used in a circuit with the switching voltages and currents are shown in the figure. The switching times TR and TF. This is a TR and a TF. Okay, are 100 nanosecond and 200 nanosecond respectively. First bit, evaluate the energy loss during on and off transitions. Okay, for the two switching schemes shown in figure. So here we are having the two switching schemes. This is the first, this one is the second switching scheme, right? Our task is to find the energy loss during on transition and off transition. Which one is the on transition, which one is the off transition? They have not mentioned. We need to check. Second, also find the switching power loss in the watt for a switching frequency of 100 kilohertz. So frequency is given. Once we get the power loss, we can find the once we get the energy loss, then we can find the power loss easily. Okay, so let us first note the data. It is given that TR is equal to 100 into 10 to the power minus 9 second. Okay, this is the TR. TF is equal to 200 into 10 to the power minus 9 second. This is the TF they have given. Okay, our task is for first bit, evaluate the energy loss during the on transition and off transition. Now my question is, for the switching scheme 1, whether TR will be your on transition or off transition. This is a TR. This is a TF. During the first switching scheme, TR will be the on transition or off transition. Come on. Voltage decreasing, current increasing. So definitely it should be on transition. Very good. It should be the on transition, right? So TR indicates the on transition. So let me write here. TR indicates the on transition. TR indicates the on transition, right? So this is a TR. Next, TF. TF indicates the off transition, because you can check current decreasing, voltage is increasing. So it is a off transition. Off transition. TF indicates the off transition. Similarly, for switching scheme 2 also you can check. This is a TR and this is a TF. Okay, TR and TF are running. So during TR you can check current, they have given sudden change. Okay, current they have given sudden change, doesn't matter, but voltage is decreasing. So from this we can say this is a turn on transition, and here voltage has suddenly changed during TF, doesn't matter, but current has decreased. Okay, so current is decreased from 20 ampere to 0 ampere, means definitely it will be a turn off transition. Okay, so for both these switching schemes, TR is the on transition, TF is the off transition, right? Turn on and the turn off transition. Okay, now let us find the energy loss. Let us find the energy loss. So now for the first switching scheme 1. Switching scheme 1. Yes. During the switching scheme 1, can we find the energy loss during the on transition? Energy loss during on transition. Energy loss during on transition. Let me write it as ETR, because TR indicates our on transition. Na? So ETR. So what you can check during TR, switching scheme 1 we are discussing. So during TR, voltage is decreasing, current is increasing. So which expression we need to use? 1/6 into V into I into TR na? This time. Correct? So this should be 1/6 into what is V? Initial voltage, that is a 400. What is current I? It is a 20 into 20 into TR is given. TR is 100 nanosecond, na? 100 into 10 to the power minus 9. So you can check this will be equal to yes 133.33 microjoule, right? This is a microjoule. ETR. It is the energy loss during the turn on transition for the switching scheme 1. Similarly, can we find the energy loss during the off transition, right? For the same switching scheme. Okay, energy loss during the off transition. Energy loss during off transition. Off transition, right? So let me write it as ETF. ETF is equal to, again 1/6. You can check during switching scheme 1, current is decreasing, voltage is increasing. Na? So same expression we can use, 1/6 into V into I into TF will be there now. So it is 1/6 into V is 400 and I is 20. So it is a 400 into 20 into TF is 200 nano, na? 200 into 10 to the power minus 9. So you can check it will be equal to 266.66, right? Simply it is double. Correct. 266.66 microjoule. This is your ETF. ETF. Is this clear? Right? Next, so what is the power loss? Power loss during on transition. Power loss during on transition. on transition is equal to switching frequency, okay, into your ETR. So you can check switching frequency is 100K and ETR is 133.33 microjoule. So it will be like 10 to the power of 5, okay. So that will be 0.1. 13.33 something, right? Yeah, 13.33 watts. Okay. Similarly, we can find the power loss during the off transition also. Power loss during off transition. Fs into ETF. 100 into 10 to the power 3 into it is a 266.66 into 10 to the power minus 6 na. So that will be your like a 26.66 watts. Okay, is this clear? So, next, similarly, we need to find for the second switching scheme. Now for second switching scheme, we cannot use that formula 1/6 because here current is constant and during this the voltage is constant. Okay, so we can simplify it. During switching scheme 2, for switching scheme 2, yes, let me write energy loss during on transition, it is turn on transition. It is ETR, no? Right? ETR is equal to integration of V into I into dt. Na? You can check during this interval 0 to TR. If this is 0, this will be your TR. Okay. So during this interval, you can check it is a V into I into dt integration. That is nothing but your integration of power is nothing but energy. So now here current is constant at 20 ampere. So we can take current outside and voltage is linearly decreasing. Okay. So let me write it as it is equal to current is constant. So I into integration of V into dt. Either you can write here 0 to TR also. What this indicates? This indicates area under the voltage curve. Okay. So it is equal to I into what is the area under voltage? 1/2 into voltage V into that TR. So if you put the values, it is a 20 into 1/2 into voltage is 400, right? Yes, 400 into TR is 100 into 10 to the power minus 9. Okay. So if you simplify it, it will be 200 into 100 into 20. This will be 400 microjoule. Okay. This is a ETR. Similarly, can we find the ETF? ETF, that is during the turn off transition. Energy lost during turn off transition. ETF, right, is equal to integration over 0 to TF. Let me write it as V into I into dt. So it is equal to in that you can check during TF. During TF, voltage is constant na 400. So I can take the voltage outside of the integration. So it is a V into integration over 0 to TF. Current I into dt. This indicates area under current curve. Okay. So which is equal to 400 into area is 1/2 into time TF is 200 into 10 to the power minus 9 into current is 20 ampere, right? You can check current is having a steady state value of 20 ampere, right? So from 20 it is decreasing. Okay, so if you simplify it, we'll be getting it as, yes, 100 into 400. 800 microjoule. This is ETF. Similarly, we can find the power loss. Therefore, power loss during TR. What is power loss during TR? It is a switching frequency into ETR, right? So it is 100K into 400 into 10 to the power minus 6. Na? So it is like 40 watt. Similarly, you can find power loss during TF, right? So it is equal to switching frequency into ETF. So it is 100 into 10 to the power 3 into 800 into 10 to the power minus 6. So it is equal to 80 watt. 80 watt. Correct? Sir, in previous class you said TR is turn on. No. It is not like that. It is not the thumb rule that TR is a turn off and TF is a turn on. No. If they give the notation TR as a turn on time, then we need to consider turn on only, na? Right? The only thing is during turn on, whether it is a turn on or turn off, how to find it? Yes, if the voltage is decreasing, current is increasing, then it is a turn on. Okay, notation will be anything, na? TR, TF. Yes, sir. Please again explain second bit. Okay. Second bit you are saying switching scheme 2. Okay. So, same straightforward. This type of numerical we discussed earlier, right? Next. Yeah, this is about the 7th numerical, right? Next now. So I think we have covered or discussed the sufficient number of numericals. Now we are moving towards the next point. Types of switches. Types of switches, right? So, already we have discussed the, strictly speaking, broadly. Okay, there are two types only. One is the ideal and second one is the practical, right? Next, again, ideal things does not exist in a real life, that we know. Okay. Next, this classification of the switches, whatever we are going to discuss now. Okay. These are related to the control techniques, and second one is based on the operating point, steady state operating point. Okay. We are having the two classifications actually. One is based on control action or the control technique. So let me put the heading. Types of switches based on control action. Okay, control action. So related to the based on the control action, there are three types of the switches. One is the uncontrolled switch, second one is a semi-controlled switch, and third one is a fully controlled switch. Okay, one is a uncontrolled, second one is a semi-controlled, and third one is a fully controlled. So now let us discuss one by one. First one is the uncontrolled switch. Uncontrolled switch. Yes. So please listen it carefully. The switch is said to be uncontrolled. The switch is said to be uncontrolled if it's on and the off, it's turn on and turn off. Okay. It's turn on and turn off. Okay, cannot be controlled by using the external signal. The switch is said to be uncontrolled if it's on and off state, that is a turn on and turn off, right, cannot be controlled by using the external signal. That is the uncontrolled switch. Let me write. The switch is said to be uncontrolled if it's turn on and turn off. Yes, cannot be controlled by using external signal. External signal. So example of this uncontrolled switch is diode. You can check in a diode. Diode turns on immediately when the forward voltage appears across it. But I am saying, yes, external signal here. Please try to understand. Don't get confused. No? External signal. Your supply voltage is not an external signal. Supply voltage is not an external signal. Okay. External signal means just like your suppose thyristor we are having or SCR. In the SCR, we are using the gate signal. That is the external signal. Your supply voltage is there only to energize the load. Na? Supply voltage is there to energize the load. The function of the supply voltage is not to turn on or turn off the switch. Are you getting the point? The main function of the supply voltage is to energize the load only. Right? So here, the switch is said to be uncontrolled if it's turn on and turn off, cannot be controlled by using the external signal. Cannot be controlled by using the external signal. So we're having the diode, right? Diode is an uncontrolled switch. Diode is an uncontrolled switch because you can check in the diode we're having only two terminals, anode and cathode, right? So whether the third terminal is present in the diode, no. And between anode and cathode, anode is generally connected to the anode and cathode are generally connected across the supply, na? Right? Anode is connected to the supply, positive or negative plate, and cathode is connected to the load, and secondary through the load we are having the supply loop completed. Okay, let me show here. Suppose we are having the circuit like this, and if we are using the diode, suppose here it is a load R, supply voltage Vs. The Vs waveform is like this, na? This is omega t 0 Vs. Omega t 0. Okay. So when Vs is positive, it is like diode will be in the forward bias mode and diode turns on. So initially before t is equal to 0, it is like diode was in a off state. After t is equal to 0, as soon as the supply voltage becomes positive, our diode will become switch into the on state. Diode will be in the forward bias mode, and diode is having the tendency that as soon as it is in the forward bias mode, it will turn on, right? So diode is turning on. Diode is switching from off state to the on state. That is nothing but diode is turning on due to this supply voltage. But this supply voltage is not the external signal. Please be careful. Okay. External signal means what? The special signal required to turn on that device. Your supply voltage is not the external signal. Supply voltage is here to energize this load. Supply voltage is here to energize the load. Are you getting the point? Right? So diode is turning on when it will become a forward bias. Okay. Similarly, if the supply voltage is negative here, it is like diode will be in the reverse bias mode and your diode will be in the off state. Okay. So you can check here during 0 to pi. It is like a diode D is in a on state, and during this interval, it is like a diode D is in a off state. So on to off and off to on, it is changing with respect to supply voltage. I am again repeating, supply voltage is not the external signal. External signal is like your gate signal. External signal is like your base current. In the case of BJT, you are having the base current. External signal is like your in the case of MOSFET, you are having the voltage VGS, na, get to source voltage. These are the external signals. But in the case of diode, yes, simply when diode is in the forward bias mode, it is turning on. When it is in the reverse bias mode, it is turning off. But in order to turn on, whether we are using the external signal here special, no. So diode is the uncontrolled switch. Please be careful. Diode is the uncontrolled switch, right? In what category? Our conventional household switch. Conventional household switch, these are our mechanical switches, right? And we are discussing about the electronic switches. Okay. So, right. So this is the diode. Diode is the uncontrolled switch. This is the one important conclusion. Next, second, semi-controlled switch. Second one is the semi-controlled switch. Semi-controlled switch. Yeah. The switch is said to be semi-controlled. Switch is said to be semi-controlled if it's on to off transition. Okay, that is a turn on and a turn off. Okay, if it's turn on or a turn off, or I'm using. Okay, the switch is said to be semi-controlled if it's turn on or a turn off, can be controlled by using external signal. I'm saying or there. Okay, so switch is said to be semi-controlled. Switch is said to be semi-controlled if it's turn on or turn off, can be controlled by using external signal. So I'm saying either on or off, okay, can be controlled by using the external signal. One example is SCR, silicon controlled rectifier. You can check in the SCR, we can turn on the SCR by using the gate signal. But if we remove the gate signal, whether the SCR will turn off? No. Are you getting the point? So that's why SCR is a semi-controlled switch. In the SCR, we can turn on the SCR by circulating the positive gate current in the gate cathode circuit. Na? Okay, means circulation of the gate current is turning on the switch. But if we remove the gate signal, or if I reduce the gate current to the 0 ampere, whether our SCR is turning off? No, right? So that's why SCR is a semi-controlled switch. SCR is a semi-controlled switch, right? Let me write here. Yes, by circulating positive gate current, SCR turns on. But if gate pulse is removed, that is nothing but gate current 0. Okay, but if gate pulse is removed, SCR will not turn off. SCR will not turn off. That's why it is a semi-controlled switch. Right? And next we are having the fully controlled switch. Next one is the fully controlled switch. Fully controlled switch. Okay. So, now in the uncontrolled, yes, neither on state nor on state was controlled, right? In the semi-controlled, either or off was there. Okay, now fully controlled means the switch is said to be fully controlled if it's on state, that is a turn on, and a turn off, can be controlled by using external signal. I am using the word and here. Okay, switch is said to be fully controlled fully controlled if it's on, that is a turn on. If it's turn on and turn off can be controlled by using external signal. Okay, by using external signal. External signal means on as well as off, both these states, okay, can be controlled by using external signal. Examples, we're having number of examples in the fully controlled: BJT, right, IGBT, MOSFET, GTO, right, etc. These are the fully controlled switches. You can check in the BJT, if the base current is above the threshold value, our BJT turns on. If it is less than that of threshold value, BJT will not turn on. Means if base current is greater than threshold, BJT turns on. If it is less than threshold, it turns off. Means its total turn on and turn off is controlled by the base current. Na? In the MOSFET, we are having the VGS voltage, gate to source voltage. If VGS value is greater than the threshold value, MOSFET turns on. If VGS value is less than the threshold value, MOSFET turns off. Na? Right? Means VGS controls the turn on and turn off of the MOSFET. So that's why MOSFET is a fully controlled switch. Similarly, in the case of GTO, you can check. GTO is similar to your SCR only, but advantage is that in the GTO, by circulating the positive gate current, I can turn on the GTO, and by circulating the negative gate current, I can turn off the GTO. So by using the gate current only, I am turning on and turning off the GTO. So that's why it is a fully controlled switch. Is this clear? Thyristor, already we have discussed. Thyristor means generally SCR we consider. Okay. So SCR is a semi-controlled switch. It is not a fully controlled switch, right? Okay. Relay switch is comes that will be your relay will not be here in the power electronics. Ankur. Any other example else? SCR for the semi-controlled, you can check the your TRIAC. TRIAC is a semi-controlled switch. TRIAC is like anti-parallel connection of two SCRs, right? Okay. Next, so this is a classification based on controlling action. Based on controlling action. Okay. Now we are going to discuss the next classification. Basically, it is based on. Okay. Yeah. Next classification is based on operating points, or you can say the steady state operating points. Steady state operating points. So there are 4 types actually. First one is unipolar switch. Unipolar switch. Second one is a bipolar switch. Third one is the unidirectional switch. And fourth one is the bidirectional switch. Okay, these are the 4 classifications. For unipolar and bipolar, okay, these are associated with the turn off state, or let me write it as a blocking state. Turn off, or we can say the off state. Just a minute, note is not responding. Okay, yes. So for unipolar and bipolar, we need to concentrate on off state of the device or blocking state. Blocking state of the device. Okay. Unidirectional and bidirectional, we need to focus on state or conduction state. Or conduction state. Okay. So yes, so let us first discuss what is the unipolar switch, right? Unipolar switch. The switch is said to be unipolar if it blocks either forward voltage or reverse voltage during its off state. I am saying the switch is said to be unipolar if it blocks either forward voltage or reverse voltage during its off state. Okay, so unipolar switch, it blocks either forward voltage or reverse voltage during its off state. During its off state, right? The switch is said to be unipolar if it blocks either forward voltage or reverse voltage during its which state? Off state. During its off state. So suppose we are having a switch in a off state. For example, suppose SCR is in a off state, and if it is blocking the forward voltage, okay, or reverse voltage, then we can say that SCR is a unipolar switch. Okay, but our SCR is not a unipolar switch. You will understand while discussing the SCR. Okay, so now next, this is the unipolar switch. Now let us discuss the static operating point on VI plane for the unipolar switch. Okay, static operating point on VI plane. Static operating point. They have asked the questions GATE, ESC as well as for PSUs. Okay, static operating points on VI plane or location of static operating points on VI plane we can see. Okay, so before that, just a minute. One thing is there, uncontrolled switch, that is a diode. As these are uncontrolled now, so these are known as the passive switches. Uncontrolled switches are the passive switches. Semi-controlled and fully controlled, these are the active switches. These are the active switches, right? Sometimes they use the word like active switch and passive switch. Okay, so always keep in mind, passive switch means it is an uncontrolled switch. Okay, and active switch means either it is a semi-controlled or fully controlled. Okay, now next, static operating points location on VI plane for the unipolar switch, right? So as long as the unipolar and bipolar switches are considered, okay, this classification is considered. On which state we need to concentrate? We need to concentrate on off state. Yes or no? Off state only, right? So off state means what? Switch is in a off state. Switch is in a off state. So what is the current flowing through the switch? Ideally speaking, it should be zero now. Current flowing through the switch will be zero. Yeah, let me indicate. Current flowing through the switch is zero. So current flowing through the switch is zero means your static operating point should lie either on the plus V or on the minus V. Okay, suppose if I indicate it is at the minus V, if I indicate at the minus V, okay, or second possible operating point location on the VI plane for the same unipolar switch, okay, is like this, either here or here. So this is the voltage and the current, right? Here it is negative V, here it is a positive V. Here it is a positive V. Please try to understand what is the meaning of this point. This point, what it indicates. This point is lying on the negative V axis. Okay. corresponding to this point, what is the current? You can check. Corresponding to this point, the coordinates are, it is like a minus v comma 0 na. X coordinate is minus v, y coordinate is 0. The meaning is current is 0. Current is 0. Current 0 means switch is in a off state. Yes or no? Current is 0 means switch is in a off state. And voltage across switch is minus v. The meaning is the switch is in a off state and the voltage across switch is minus v. The meaning is the switch is blocking that voltage. Switch is blocking that voltage. Are you getting the point? Switch is blocking the minus v voltage means what? Switch is blocking the reverse voltage here. Similarly, you can check for this point. What is the coordinates of this point? X coordinate is v and y coordinate is 0. The y coordinate indicates it is a current na. Y coordinate indicates current. So current is 0. The meaning is switch is in a off state. So switch is in a off state and voltage across switch is v na plus v. The meaning is switch is blocking the forward voltage. So this indicates switch is blocking the forward voltage. This indicates switch is blocking the reverse voltage. So that's why unipolar switch means either blocking the forward voltage or blocking the reverse voltage, but not the both na at the same time. Yes. So unipolar means either forward or reverse. So that's why these are the static operating point locations on VI plane for the unipolar switch. Is this clear? Right? So now, whether we are having the switch which is having this type of blocking capacity, or you can say the static operating point location, we are having a diode. Example, diode. Yes or no? Diode blocks the reverse voltage, na? Right? So that's why here this operating point is valid for diode case, in the case of diode. Similarly, whether we are having the switches which blocks the forward voltage, only forward voltage, I am saying only forward voltage. Yes, we are having a BJT, we are having a MOSFET, we are having a IGBT. That is nothing but transistor family members. Okay, transistor family members, they blocks only forward voltage during their off state. Okay, so examples are BJT, MOSFET, IGBT, right? IGBT. Is this clear? So this is the unipolar switch. Similarly, let us discuss for bipolar switch. Second one is the bipolar switch. Bipolar switch. Yes. The switch is said to be bipolar if it blocks forward as well as reverse voltage during its off state. During its off state. Okay, so it blocks forward as well as reverse voltage. Forward as well as reverse voltage during its off state. During its off state. Right? So let me highlight forward as well as reverse. So it blocks the forward voltage and at the same time reverse voltage also during its off state, forward as well as reverse. Okay. So now how will the static operating point location on the VI plane for the bipolar switch? Yes, static operating point location. Static operating point on VI plane. Right, on VI plane. It will be like this is a voltage, it is a current, right? V and I means voltage across switch and current from the switch. Okay, so switch blocks forward voltage as well as reverse voltage during its off state. Off state means definitely current will be 0, right? So operating point will be here and here. Are you getting the point? Corresponding to this point, you can check the coordinates are V and 0. So current 0, voltage across switch is positive na. So switch is blocking positive voltage, right? Similarly, corresponding to this point, voltage is negative and current is 0. Current 0 means switch is in a off state, right? Current 0 means switch is in a off state and voltage across switch is negative means what? Switch is blocking the reverse voltage, right? So it is the forward voltage blocking. This is the reverse voltage blocking. So whether we are having the switches which are the bipolar, means during their off state, they blocks the forward voltage as well as reverse voltage. Yes, we are having the SCR na. SCR examples. SCR is there, GTO is there, right? SCR, GTO, and TRIAC is also there. TRIAC. This blocks the forward as well as reverse voltage during their off state. Right? Next, here important word is the off state. Off state is very important. Okay. So next, let us discuss for unidirectional and bidirectional switch. Okay. Next one is the unidirectional and bidirectional. Unidirectional and bidirectional. Right? So in that, first discuss the unidirectional. Let me write unidirectional only. Yes. The switch is said to be unidirectional if it allows current in only one direction during its on state. Okay. Unidirectional switch allows current in only one direction during its on state. Means one direction means either forward, either positive current or negative current. Okay. So it allows either positive current or negative current, positive current or negative current, either positive current or negative current during its on state, right? So important, yes, here the switch should be in the on state and it is allowing either positive current or negative current, either positive or negative, I am saying. So how will be the location of static operating points on VI plane? Yes, we can indicate it as positive current or negative current. Na? So this is voltage, current. Similarly, voltage and current, right? So switch is in a on state. Switch is in a on state means what about the voltage across the switch? Yes, theoretically it should be zero now, right? So voltage across switch is zero means the operating point should lie on current axis only. Okay. So suppose operating point is at this point, at this location. The meaning is corresponding to this point, if you check, coordinates are 0, x coordinate is 0 now, and y coordinate is I. So x coordinate 0 means this is a voltage coordinate, right? V coordinate. So V is 0 means voltage across switch is 0. Voltage across switch is 0 means switch is in a on state, right? And current flowing through the switch is positive. The meaning is switch is in a on state and it is allowing the positive current. It is allowing only positive current, right? Similarly, second possibility is we can indicate here either positive or negative. Okay, either positive current it is allowing or negative current it will allow, right? So corresponding to this, the coordinates are 0, minus I, right? Here, this indicates the voltage across the switch. Voltage across switch is 0 and switch is allowing the negative current, right? So that's why it is the unidirectional switch. That's why it is the unidirectional switch. Example for this, okay, for this static operating, whether we are having the switches, those allows the unidirectional current. Yes, we are having SCR. SCR allows unidirectional current. BJT, it allows unidirectional current. MOSFET, right? After that GTO, after that BJT is over, right? MOSFET is over, IGBT. All these are unidirectional switches. All these are diode is also unidirectional switch now. These are the unidirectional switches, right? Now whether we are having the switches which allows the negative current only, these switches allows the positive current now, right? These switches allows the positive current. What about the negative current? we don't have the switch that allows only negative current. I am saying only negative current. We don't have the switch. We are having the switches, those allows the positive as well as negative current. But the switch which allows the only negative current, that switch we don't have. Generally, we will not concentrate on that concept now, because negative current is generally not required for us. Okay, our function is switch should allow the forward current. Okay, that is our task actually. So next, the second one is the bidirectional switch, right? Bidirectional switch. Fourth one, bidirectional switch. Yes, the switch is said to be bidirectional if it allows positive as well as negative current. Okay, during its on state, it allows positive as well as negative current during its on state. During its on state. Okay, so it allows positive as well as negative. Okay, positive as well as negative during its on state. Okay, so how is the static operating point on VI plane location? So it will be like this. This is a voltage, current, positive current as well as negative current. It allows positive current as well as negative current. So you can check corresponding to this, the coordinates are 0, I, 0, minus I. 0 indicates switch is in a on state. That is voltage across switch na. So switch is in a on state, and switch is allowing the positive current, switch is allowing the negative current. Is this clear? So this is the bidirectional switch, static operating point on VI plane. Example, we're having a triac. Triac allows current in both the directions. Na? Triac allows current in both the directions. Is this clear? So this is about the classification of the switches, right? Classification of the switches. Diode is not a bipolar switch. Okay, someone has written diode is a bipolar. No, diode is not a bipolar switch, right? Diode is a in your EDC you might have studied the concept bipolar and unipolar. It was the different. This concept is different. Don't get confused about that bipolar concept in EDC and here it is a bipolar concept in EDC. In EDC you might have studied that BJT is a bipolar because in its name itself, na, bipolar junction transistor. But that bipolar was like is due to when the current flows through the current circulation in the BJT is due to both the charge carriers, na, positive and negative. That's why that was the bipolar in EDC. But here the bipolar concept is like when it is blocking the positive as well as reverse voltage. Okay, then it is a forward as well as reverse voltage. Then it is a bipolar. Don't get confused. In power electronics, the bipolar is having the different meaning. Right? Yeah. Yes, dioc is also bidirectional. You can say dioc is also bidirectional. Dioc is a uncontrolled switch. Okay, dioc is a uncontrolled switch. It is a bipolar, bidirectional. It is a bidirectional, right? Next. Zener is there, but that Zener is a part of your basic electronics, right? It is not a part of power electronics. We are discussing about the power electronic switches, power switches, right? There you will not get question like Zener is a unipolar or bipolar switch in a power electronics, I'm saying. Okay, so Zener is not there in power electronics, right? In the power electronics, we are having varistor, just like your Zener characteristic, we are having the varistor. We'll discuss it later on. Okay, so while discussing the thyristor, you will understand. Yeah, Mangesh, I will answer your question later on. Okay. Sir, how can we know that particular switch are unipolar, bipolar? So you will understand it while discussing the characteristics of the that switch. Yet we have not started the switches, na? After this discussion, we will discuss our some numericals, and after that we will be moving towards the first switch, that is the diode. We'll be discussing about the signal diode, and next we'll be moving towards the power diode. And after that, your thyristor, BJT, MOSFET, all switches will come. Okay. So enough for today, sir. No, we'll continue till we are having the time still. Okay. So yes. So is this clear? Next, now let us discuss device by device operating points. Okay, device operating points. That is the operating points for various devices we are going to discuss. So let us start with the diode, right? Let us start with the diode. Definitely in detail, we are going to discuss about the diode. Okay, its operation, its static VI characteristic, and as well as its dynamic VI characteristic we'll discuss. Okay. Now, this is whatever we are discussing here. This is required to solve the numericals which we are going to discuss regarding the static operating point and as well as the safer operating area location. Okay, they have asked this type of questions. So diode, whatever we are discussed just now, diode is a uncontrolled switch. Yes or no? Diode is a uncontrolled switch, or you can say that it is a passive switch, right? Passive switch. Second, whether diode is a unipolar or bipolar. You can check diode is a unipolar or bipolar. Diode blocks only reverse voltage, na? So diode is a unipolar switch. Next, diode is a unidirectional or bidirectional. Diode is a unidirectional switch. Okay, so it is unipolar and unidirectional switch. Unipolar and unidirectional switch, right? How is the symbol of diode? This is the symbol of a diode. Anode, cathode. Okay. And how is the static operating point location on VI plane? It is like this. Voltage, current. In the case of diode, just now we discussed the, yes, diode allows current in only positive direction and it blocks only negative voltage, na? Whether diode blocks positive voltage? No, right? Diode blocks only negative voltage and diode allows only positive current. Okay, so from this we can show the SOA, that is the static operating area. Okay, this is the SOA for a diode, right? Or safer operating area for a diode. Okay, SOA. So SOA of a diode, SOA of diode is in which quadrant? Second quadrant. Is in second quadrant. Is this clear? What the SOA indicates? SOA indicates the maximum voltage. This point indicates the maximum voltage that can be blocked by the diode, and this indicates the maximum current that can be allowed by the diode. Okay, so maximum current allowed, maximum current voltage blocked. Okay, maximum voltage blocked, maximum current allowed. And from these 2 points, yes, we have drawn the SOA. Second, next device we are having transistor family devices like your, yes, BJT, MOSFET, right? BJT, MOSFET, right? IGBT, BJT, MOSFET, and IGBT, right? Let us discuss for these devices. The symbol of the BJT we know. We are going to discuss in detail about the BJT. Okay. Right, emitter, this is your collector, and this is the base. Okay, sorry, this should be the emitter here. C here and E here, right? This is the BJT. Next, MOSFET symbol. MOSFET is a voltage controlled device. Yes or no? Let me show, indicate here. Yes. Terminals are gate, source, and here it is a drain. Okay, this is a BJT. This is a MOSFET N channel. I have shown only one MOSFET here, and the IGBT. IGBT is like a combination of, right, these two. Okay, these two devices. This is a gate, collector, and emitter. Okay, this type of, this is IGBT variant. Next, if you check the MOSFET, BJT, and IGBT, this allows current in only one direction. Okay, and they blocks voltage in only they blocks voltage only of positive polarity. Now we discussed. You can check here. We have written, yes, BJT, MOSFET, and these things. Okay, they blocks only positive voltage. Okay, and allows current in only one direction. Okay, that is this one, right? BJT, MOSFET, and these things. So let me draw their static operating points on VI plane. This is a voltage, this is a current, allows only positive current, blocks only positive voltage, okay, during their off state. So this is a SOA. SOA for this transistor family devices. SOA is in which quadrant? It is a first quadrant. SOA is in first quadrant. First quadrant, right? Next, SCR. Let us discuss for SCR. Silicon controlled rectifier. And GTO. GTO, right? So SCR and GTO. The symbol of SCR is like this: anode, cathode, and gate. Okay, anode, cathode, and gate, right? And the symbol of GTO is GTO is having three valid symbols actually. Same anode, cathode, gate. Okay, this is the symbol of the GTO. This is for SCR. Second symbol is like this. Gate, and the next symbol is like this. Okay, so this type of symbol. One is for positive gate current, second one is for negative gate current, right? One is for positive, second one is for negative. Positive is for turn on the GTO, and negative is for turning off the GTO. So this is these are the three valid symbols of the GTO. You can check symbol of GTO. Let me reduce it to 45. Right? So this indicates one current is positive, second one is negative. Here it is like a positive negative, means they have simply put one line here, and here it is positive negative current. Okay, so GTO. Now SCR and GTO, if you check, these are the bipolar switches now, and it allows current in only one direction. So this is a current, voltage. Here it should be voltage, and here it should be current. Okay, it blocks positive as well as negative voltage and allows current in only one direction. So where will be the SOA? SOA will be, yes, in first and second quadrant, right? This is a SOA. SOA is in first and second quadrant. They have asked the question, okay, the SOA of the diode is, keep it in mind, it is the second quadrant, right? And last device we are having, that is trike, okay. Trike is a bipolar bidirectional switch. This is the voltage and the current, okay. So it is a bipolar and a bidirectional, bipolar and bidirectional, right? So symbol of a trike, so you can check SOA for trike is all the four quadrants, right? All the four quadrants is a SOA for the trike. SOA is all four quadrants. All four quadrants. The symbol of trike is like this. Trike is equivalent to antiparallel connection of two SCRs. Okay, so it is like this. But it is having only one gate terminal, right? Anode, cathode, and here it is a gate, right? This is the symbol of a trike, right? So this is about the devices and their operating point location, okay, or the SOA you can say, right? Let us discuss some numericals related to this. SOA means the safer operating region or area, right? So SOA for trike. Next, let us discuss the numericals. Yeah, before that, let us discuss one concept with MOSFET and IGBT with body diode. MOSFET and IGBT with body diode. Okay, so what is the body diode? That you will understand while discussing the MOSFET and the IGBT. Now only I will show you how it is indicated, okay, and how it will be changing the static VI point locations, okay, for the MOSFET and the IGBT. So first, MOSFET with body diode, okay. So MOSFET with body diode. So MOSFET with body diode means it is like a inbuilt diode is there. Okay, inbuilt diode is there. This is not the externally connected. Please don't get confused. Okay. This is your MOSFET. Pawan Kumar, do you want to say something?
Sir,
Yes, please.
no doubt, sir. But in the class notes uploaded, they are somewhat clumsy, sir. That's all.
What?
Yesterday class notes you uploaded, no, sir.
Yes.
That was somewhat clumsy, sir.
Okay. Now the thing is, actually I am directly converting that OneNote to the PDF. So
Okay.
that was, it is not means what I can say, the equal mapping is not there. I think in PDF it is taking only for that A4 size something. Okay, I will check, and if possible, if our OTS accepts that OneNote file, then I will try to upload that OneNote file directly. Okay.
Okay, sir.
Yes.
Thank you, sir.
I will check. The MOSFET with the body diode. Okay, so same gate terminal, source terminal, and drain terminal wiring. Okay, gate, source, and drain terminal. MOSFET with body diode, and it is having the VI characteristic like this. It is like a combination of VI, we cannot say VI, static operating point location. It is combination of MOSFET and the diode, combination of MOSFET and the diode. So it is a V, it is a I. You can check due to this diode, whether the reverse voltage will be blocked. No, but reverse current can be allowed. Okay, so it will be like this. We'll discuss while discussing the numericals again. Okay. This is a SOA for MOSFET with body diode. Generally, the manufacturer gives the voltage and current withstanding capacity of this body diode. Okay. What is the body diode and those things you will understand it while discussing the MOSFET. Okay. I'm repeating it again. SOA is in first and fourth quadrant. And similarly, we are having the IGBT with body diode. IGBT means insulated gate bipolar transistor with a body diode. We're having the insulated gate, remaining two terminals of the transistor. Okay. Here it is a collector, emitter, and here it is a gate. Okay. And here it is a body diode. Right. This is a body diode. This is not the external diode. This is the inbuilt diode I am saying. Okay. Yes. The static operating point location on VI plane. Again, it is the same as that of the MOSFET. It operates in first and the fourth quadrant, right? SOA is in first and fourth quadrant. Okay, so this is the devices with the body diode. Okay, and their static operating points on VI plane and the quadrant of operation actually. Okay, so now let us discuss some numericals related to this static operating point on VI plane. Yes. Composite switch means multiple single quadrant switches are connected in different configuration to get multi-quadrant safer operating area. Okay, SOA means we're having the switches which operates in a single quadrant, and if I club these two switches, I will be getting the multi-quadrant operation. That total combination of the switch, okay, is nothing but your composite switch. So composite switch consists of, yes, multiple switches, right? It may be like a thyristor is connected in parallel with the SCR. Thyristor is connected in parallel with the SCR. You can check one example I am writing. Suppose we are having a SCR and it is connected in parallel with the diode. SCR is connected in parallel with the diode. So for example, suppose if this is the our SCR, and here I am connecting the diode here, anti-parallel. So let us discuss how to find its the static operating point location. Okay, static operating point location. Consider this full as a single switch. I am saying consider this full as a single switch. This is a single switch only because this is a composite switch, na? Consider it as a single switch. Okay, so while identifying the static operating points on the VI plane, means what? We need to check whether the switch is unipolar or bipolar, and whether it is a unidirectional or bidirectional. That we need to check, because unipolar, bipolar, and unidirectional, bidirectional, these only, yes, gives you the location on the static operating point location of the static operating points on VI plane? Yes or no? Right? So now let me draw first the plot, that is the voltage across the switch and the current flowing through the switch. So let me write here. This is the current axis and this is the voltage axis. So this is the V and this is the I. This is the voltage and this is the current. So now one thing, as we have discussed regarding the SCR, right? While discussing the unipolar, bipolar and unidirectional, bidirectional. So if you check, SCR is it is a bipolar switch and it is a unidirectional switch. Na? SCR is a bipolar switch and it is a unidirectional switch. So here if you check, for the SCR, can I draw the VI character, that static operating points? For SCR alone I am saying. For SCR, can we draw the static operating points on VI plane? The same thing we already drawn, V and I. For SCR it is cross here and here it is, right? And we know we have written SCR is a bipolar and unidirectional switch. This is for SCR only. Means SCR blocks the positive voltage, negative voltage and positive current it allows. Okay. Now we are having the points like this is the A, this is the B. The positive voltage means what? Positive voltage means it indicates, yes, positive voltage means it indicates plus here and minus here. Yes or no? Positive voltage means A is positive, B is negative. Similarly, if you check for SCR, here it is an anode and here it is a cathode, right? We are having anode here and cathode here. So anode, when voltage is positive, that is when A is positive and B is negative, it is like a higher potential is appearing at the anode of the SCR, lower potential is appearing at the cathode of the SCR. So can we say that when voltage is positive, it indicates the voltage across SCR is also positive. Voltage across SCR is also positive. Means if VAB is positive, voltage across SCR is positive. But what about the voltage across diode? Whether it is a positive or negative, you can check, because to the terminal A, here we are having the cathode of a diode now, and to the terminal B, we are having the anode of a diode. So can we say that when VAB is positive, yes, it is like a cathode is at higher potential, anode is at lower potential. So it is like voltage across diode is a negative. Are you getting the point? Please try to understand. Let me write this. Yes, if VAB is a positive, if VAB is positive, voltage across SCR, voltage across SCR is positive. But what about voltage across diode? Voltage across diode is negative. Voltage across diode is negative. Are you getting the point, right? So voltage across SCR is positive. VAB positive means voltage across SCR positive, right? And voltage across diode is negative. Similarly, if VAB negative, what will happen? If VAB negative means voltage across SCR is negative and voltage across diode is positive, right? Similarly, let me write, if VAB is a negative, if VAB is negative, it is like a voltage across SCR. Voltage across SCR is a negative and voltage across diode is a positive. Voltage across diode is positive. Similarly, check for the current. Check for the current. Okay, suppose the current in this direction A to B, current A to B is nothing but for our composite switch. Okay, current A to B, that is the current I, is the composite switch, is the positive current for our composite switch. This is a composite switch now. So if the current is flowing from A to B, so for our composite switch, this current is positive. Okay, so if I is positive, let me write, if I is a positive, if I is positive, that is our composite switch current is positive, then what will happen? What about the SCR? When composite switch current is positive, then can we say that SCR current is also positive? Are you getting the point? SCR current means what? If current is like this, then current is flowing like anode to cathode, na? So SCR current is also positive. So can I say that SCR current is also positive? SCR current is also positive. But what about the diode current? For diode, you can check for diode. The current direction is, if current is in this direction, for diode the current direction is from cathode to anode. Na? If diode, for diode current direction is cathode to anode, means whether it is a positive current or negative current for diode, it is a negative current. Are you getting the point? So for diode it is a negative current. For diode it is a negative current. Okay, so if current is positive, SCR current is positive, diode current is negative. Second, if current is negative, okay, that is current is negative means composite switch current is negative. That is, this current is minus I actually. If current is negative, then can we say that SCR current is flowing from cathode to anode, means it indicates the negative current for the SCR, and the current for the diode is from anode to cathode. Now, if current direction is like this, then for the diode, the current will be from anode to cathode. So anode to cathode current for diode, whether it is a positive or negative current, it is a positive current. Okay, so let me show. Let me write. When current is negative, SCR current is negative. And what about the diode current? Diode current is positive. Diode current is positive. Now, yes. So here you can check for the SCR. Yes. So can we write for the SCR here? You can check if composite switch, VAB indicates what? Composite switch voltage. Composite switch voltage. So if composite switch voltage is positive, SCR voltage is also positive. If composite switch voltage is negative, SCR voltage is also negative. If composite switch current, this I is nothing but composite switch current. Composite switch current. Okay. If composite switch current is positive, SCR current is also positive. If composite switch current is negative, diode current is, if composite switch is positive, if composite switch current is positive, diode current is negative, right? If composite switch current is negative, SCR current is negative. Means can we say that the voltage and current of composite switch and SCR both are in the same direction? Yes or no? Composite switch voltage positive, your SCR voltage positive. Composite switch voltage negative, SCR voltage negative. Composite switch current positive, SCR current positive. Composite switch current negative, SCR current negative. But in the case of diode, it is opposite, right? If composite switch voltage is positive, diode voltage is negative, because diode is connected in anti-parallel. Between A and B, we have connected the diode. Okay. So now for diode, can we draw the VI static operating points on the VI plane? Can we locate? In the case of SCR, we have located directly, because voltage and current polarities for SCR and the composite switch both are same. But in the case of diode, it is not like that. Now you can check. So how we do the composite switch for the diode? Static VI point, VI point location on the, yes, static point location on the VI plane. Yes, for diode I am saying. This one is for SCR we have written. Now we are discussing for the diode. This V indicates your composite switch voltage. I indicates composite switch current. Now please, yes, can you tell me, if composite switch voltage is positive, whether our diode will be in the forward bias mode or reverse bias mode? Please listen it carefully. When the composite switch voltage is positive, means anode is positive, B means A is positive, B is negative. The diode will be in the forward bias mode or reverse bias mode? Reverse bias mode, yes or no, right? So diode will be in the reverse bias mode. So here can we say that when VAB is positive, diode will block that voltage? Yes or no? Because diode is in the reverse bias mode. So here let me show the VI static operating point on VI plane for the diode is like it is blocking this positive voltage. Don't get confused. This V indicates voltage across the composite switch. Voltage across the composite switch. The voltage across composite switch is positive. The meaning is our diode is blocking that voltage because diode is in reverse bias mode, right? Second thing, suppose if VAB is negative, VAB negative means B is positive, A is negative. If B is positive, A is negative, what about the diode? Diode will be in the forward bias mode or reverse bias mode? If B is positive and A is negative, diode will be in the forward bias mode or reverse bias mode? Come on. If B is positive and A is negative, diode will be in which mode? Forward or reverse? Forward bias, yes or no? I am saying B positive and A negative. So your voltage across composite switch is negative. If voltage across composite switch is negative, voltage across diode is positive. So diode will be in the forward bias mode. So if the diode is in a forward bias mode, whether our diode will block that voltage? No. So always keep it. So here, please check the operating point on VI plane. Yes, whether it will be at the minus V? No, it will not be at the minus V. Are you getting the point? So it will be here only. Now check the unidirectional, bidirectional. So when composite switch current is positive, for diode it is like a reverse current, na? So whether our diode will allow the reverse current? No. Yes or no, diode will not allow the reverse current. Okay. And when composite switch current is negative, that is from B to A, for the diode, that current will be the positive current, right? So diode will allow that current, means this current will allow, right? Diode will allow this current. That is the negative current for composite switch I am saying. Okay. Negative current for composite switch, the diode will allow. And the positive voltage for composite switch, diode will block. So this is for diode, VI static operating point. And this is for SCR. This is for SCR, right? So if we club it, then what will happen now? Let us discuss. Okay. Now let us discuss, right? So important thing is our SCR can block. Okay. Suppose let us consider this point. Means voltage is positive and A is positive, B is negative. A positive, B negative, right? And if SCR is in an off state, SCR is active switch, na? If SCR is in an off state, so definitely SCR will block that voltage. Please check if A is positive, B is negative, whether diode will block that voltage. Yes, diode is also blocking that voltage. Are you getting the point? Means our composite switch will block the forward voltage. Now suppose A is positive, B is negative, SCR is in a forward bias mode, and if I circulate the gate current, our SCR will start conduction. So that's why current will be flowing like this, na? Right? So our positive current will be flowing through the SCR. Right? Next, what about the when voltage is negative? Voltage negative means here it is plus and here it is minus. If here it is plus, here it is minus. Whether this voltage can be blocked by our diode? No, diode will not block that voltage. Are you getting the point? Because diode will be in the forward bias mode. So that's why whether the operating point will be here? No, operating point will not be here. Because diode will not block that voltage, na? Reverse voltage. Diode will allow the current. Diode will immediately turns on. So diode will not block that reverse voltage. Means for composite switch, it is a reverse voltage. That will not be blocked. Right? And what about the minus I? When current is in this direction, that will be flowing through the diode. So that's why it will allow the negative current also. So you can check this switch combination is a unipolar and bidirectional. Right? SCR was blocking the negative voltage also, but diode is not blocking the negative voltage, na? That is the thing. When voltage is negative, diode will be in the forward bias mode. So that's why here operating point will not be there. You can check. It is very simple. When voltage is positive, it is like plus here, minus here. When SCR is in an off state, SCR is active switch, na? When SCR is in an off state, definitely SCR will not allow current through this. Means SCR is blocking that voltage. And when A is positive, B is negative, diode will be in the reverse bias mode. So that's why our composite switch will block that positive voltage. So that's why here the operating point. Similarly, now you can check. When voltage is positive and if the gate current is applied to the SCR, gate current is circulated, gate pulse is applied to the SCR, our SCR will turn on. So that's why the positive current will be circulated through the SCR. So positive current will pass through the SCR means our composite switch allow that positive current. Now you can check for the negative voltage, that is plus here and minus here. Our diode will allow the current, na? Our diode will be in the conduction mode. When B is positive, A is negative, diode will be in the conduction mode. So diode will not block that voltage. So that's why our composite switch is not blocking that voltage. Not blocking the meaning is, yes, in the composite switch the current is flowing. In the composite switch current is flowing. And similarly you can check for the negative current, right? Negative current is circulated through the diode. So that's why here it is operating point. Is this clear? So let me write here at this point. Yes, who is blocking this voltage? Diode is in the reverse bias mode. SCR is in a forward blocking mode. Okay. Which are the modes of operation of the SCR? You will understand it while discussing the SCR. Okay. Right. So static VI characteristics of the SCR. At that time you will understand. Okay. So here I am writing simply SCR is in a forward blocking. That is the off state. Blocking means off state. And diode is in a reverse blocking. Reverse blocking. Now here who is conducting? Diode is conducting. Diode conducting. Here, yes, SCR conducting. Or SCR on. Right? When V is negative, yes, diode will allow the current. Right? Diode will not be allowing the composite switch to block that voltage. Right? Because diode will be in the on state. Diode is a passive switch, na? Diode is an uncontrolled switch. As soon as voltage across it becomes positive, forward bias, diode will turns, diode starts conduction, right? Yes. So it's 9:12. Okay, we're running out of time. Okay. Now you are having any doubt? Please ask. Yes, just a minute. Yeah, Pawan Kumar.
Hello, sir.
Yes, you are audible.
What exactly that blocking, sir? Forward blocking.
What?
What exactly that is forward blocking, sir? Forward blocking and reverse blocking voltage.
No, that you will understand forward blocking, reverse blocking at the time of SCR discussion. Forward blocking means SCR is in a forward bias mode, but it is in a off state.
But you in graph you are showing the voltage is there, no, sir? In steady state.
Yeah, voltage. No. Generally, the thing is when the switch is in an off state, it blocks the voltage only. Try to understand this. When switch is in an off state, it blocks the voltage. And when switch is in an on state, it allows the current.
Yes, sir. Because it is a blocking, no, sir. In graph, you are showing that some voltage is there. No?
Yes, some voltage is there, but what is the meaning of this point? You can check corresponding to this point. What is the current?
Zero.
Current is zero, na?
Okay.
Current zero means switch is in off state.
Okay. That
Right.
voltage across switch, no, sir.
Voltage across
During-
switch is there, right? Means
Okay.
voltage across switch is non-zero means the switch is blocking the voltage,
Okay.
right? Okay.
Sir, hello.
Yes.
Sir, one more thing, sir, about that morning session, sir.
Yeah. Just now, during this break time, I have informed the office person. He will discuss with you all. Okay.
Sir, once ask if anyone having this problem, sir.
No. Yes, I think before starting us, also someone raised the same issue. He will discuss with you all. Yes, Sahil.
Good evening, sir.
Yeah, good evening.
Sir, we solved one problem after the piecewise modeling.
Just a minute. Piecewise modeling. Yes, in that.
Sir, we have calculated RMS value, sir.
In the numerical.
Yes, sir.
Yeah. Which numerical you are saying?
Just
This
after
one?
the piecewise modeling.
Yes. The
Yeah,
same
yes, sir.
numerical.
Yes, sir.
In that.
Sir, we have three different formulas for RMS value. Sir, we have the under root, sir. But like, sir, yes, sir. But sir, we have taken whole under root, sir.
Yes. Because it is the combination. Na? Now here we are having the triangular plus rectangular. Are you getting the point?
Yeah.
So that's why we need to first of all find its RMS square. Its RMS square and its means we need to put the square to the power 1/2 for the whole term, not for the individual. Are you getting the point?
Yes, sir. Okay.
In this way, you can check by writing the expression for this waveform, and calculating the RMS value. Okay, by that expression, and you can compare it with whatever we have written here. You will be getting the same answer.
Okay, sir. Thank you, sir.
Okay. Yes. Yeah. Next one. Yes, Ramakrishna.
Yeah, hello, good evening, sir. So,
Yes. Good
the
evening.
doubt is composite switch one, sir. Once more, can you open the slide? I will ask the doubt.
Okay. Composite switch, no? Yes.
So, you are saying that during positive voltage, forward blocking will be there, but
Yes.
SCR can conduct the forward blocking, no, sir. So, it should also be
No.
not.
The thing is, the unipolar or bipolar. To which state we are concentrating? We are concentrating on blocking state, na?
Yes, sir.
So SCR is having actually SCR is a controlled switch.
Yes, sir.
So when we circulate the gate pulse or when we apply the gate signal, na, then
Okay,
only,
then
our
only-
SCR will start conduction.
Start. Okay, till there. So, it is in forward blocking. Okay, I got it.
Yes. Is this
Yeah.
clear?
Yes, sir. Yes. Okay.
Yes.
Thank you.
Okay.
Hello, sir.
Yes.
Sir, I didn't get this diode SOA of second quadrant operation, sir. How
Okay.
it was in the second quadrant SOA
Okay.
of diode.
Here in this example, or you are seeing in previous?
Also in the diode case.
In the diode device operating points, right?
Yeah.
Here it is the diode. Yes, this one, na?
Yes, sir.
So
How it
diode
was
is a uncontrolled switch.
yes, sir.
Whether diode blocks the forward voltage,
No.
blocks the meaning is what? Suppose if the forward voltage is maintained across the diode, whether diode will continue into the off state? No, diode will immediately turn
No,
on.
sir. For positive voltage, the current should flow, sir. The current should be
Positive
positive.
voltage?
Current should flow. Means
No.
it does not
See,
blocking
the thing is, while finding the unipolar and bipolar, we need to concentrate on which state, off state.
Yes, sir.
So suppose if I apply the forward voltage across the diode, forward voltage means anode is positive, current cathode is negative. Okay.
Yes.
So whether our when the anode is positive and cathode is negative, then diode will start immediately conducting.
Yes, sir.
Then what about the voltage across the diode?
0.
So whether
Yeah.
the operating point will be on the positive V axis? No. Are you
Okay.
getting the point? Operating point will not be there on the positive V axis in the case of diode, because these operating points on the plus V and the minus V, what they indicates? It indicates the device is blocking the forward voltage or reverse voltage. So as diode is not blocking the forward voltage, so that's why here we cannot show the operating point on the positive V axis.
Okay. And for current, sir?
For current, here we are having the Y axis, na?
Okay.
This indicates diode is allowing the positive current.
Okay.
This indicates diode is blocking the negative voltage.
Okay.
Right?
Means it is working in the first quadrants and third quadrant.
It is not working in the first quadrant. This is a safer operating area. It is not you cannot say that it is like operating points. No, it is a safer operating area. Means what? It just gives that the information that if your operating point, okay, your operating voltage will be greater than this voltage, then your diode will get damaged. If your operating current is greater than that of this current, then our diode will be getting damaged, right? So SO is specifically for limits
Okay.
voltage and the current.
Means for
right?
the this negative voltage above this negative voltage, diode will burn out. Yes, sir.
Yeah. If the negative voltage is greater than this point, then it will burn out.
Okay. Yeah. Okay.
Because the
Okay, good.
diode is having some finite voltage blocking capacity, na? That is
Okay,
nothing but the voltage rating of the diode, right?
Yes, sir. And sir, this is the power diode, no?
Yeah, this is the power diode,
Okay.
right? Okay.
Okay, sir.
Yes.
Hello, sir.
Yes, please.
Sir, can you please open the composite switch slide, sir? I will explain that.
Okay, just a minute. Yes.
Sir, can you please explain the diode characteristics, how we have written here?
This diode, na?
Yes, sir.
Actually, the
Ah.
thing is, this V is nothing but voltage across composite switch. Okay.
Okay, sir.
And means indirectly it is a VAB, na? And this I is nothing but current flowing through the composite switch. Current through composite switch. So now you can check when the voltage across composite switch is positive, then it is like voltage across diode is negative, na? Because cathode will be more positive than that of the anode. Means it is like for diode the reverse voltage will be there.
Yes, sir.
Yes. So if the voltage across composite switch is positive, then the reverse voltage is acting across the diode. So whether our diode will conduct into the reverse bias mode? No, na? So that's why
No.
here it is like when composite switch voltage is positive, our diode is blocking that voltage, right? And similarly, you can check diode whether the diode allows the reverse current. No, na?
No.
Means when the composite switch current is positive, diode will not allow the current. But
Yeah,
when
sir.
composite switch current is negative, then diode for the diode that current will be positive. Means diode will allow that negative current of the composite switch, na? That is from anode to cathode,
Yes, sir.
right? So for the diode, the negative current of the composite switch is nothing but the positive current for the diode. So that's why operating point will be here and here.
Sir, for voltage, we are taking the blocking characteristics, and for current, we are taking the
Allowing
What do we-
current is allowing. That is
allowing
constant.
characteristics.
Conduction state.
So for current, it is the conduction. For voltage, it is the blocking, sir.
Yes. For
To
voltage, it is a-
estimate the safe operating area.
Yes.
Sir, and also please explain the composite switch characteristics, sir.
This composite switch characteristic. Okay.
Yes, sir.
This one, na? Okay.
Yes.
So same, you can check this V indicates V positive matlab means VAB is positive. V negative means VAB is negative. Okay. So whether if I
Okay.
want to find whether the point is lying on the V plus V or minus V or not. Okay. So in that case, we discussed this plus V point or the minus V point, what it indicates, the unipolar or bipolar it indicates, yes or no, right?
Yes,
So
sir.
here you can check if V is positive, if my point is here, okay, V is positive. So V positive means anode is A is positive, B is negative. If A is positive, B is negative, the thing is whether the diode will allow the current. No, diode will block the
No.
voltage, na, because the reverse bias.
Yes,
Second
sir,
possibility
diode
is
blocks.
check with the SCR. Check with the SCR. So when suppose SCR is in a off state, SCR is in a forward bias mode, no problem, no doubt. But SCR is in a off state. SCR is in a forward bias mode, but it is in a off state because SCR is an active switch. We know, na? It is a controlled
Yes, sir.
switch. As long as soon as
Gate
it
pulses is given.
Yes, gate pulse is applied, then only then it will turn on, right? So SCR is in a off state, diode is in a reverse bias mode. So when VAB is positive, whether the current will flow through the switch? No. So that's why it is like our
No.
switch is blocking that voltage. That's why here. Now
Okay.
you can check for the negative also. Or suppose let us first find for the current. Okay. So suppose VAB is plus here, minus here. SCR is in a forward bias mode. And if I now apply the gate pulse to the SCR, then whether the SCR will allow the current through this path?
Yes, sir.
Yes. So that's why positive current will be flowing. Similarly, check for the negative voltage. So it is a plus here and minus here. So if it is plus here, minus here, okay. So it is like
Diode
SCR
will allow.
will be in the reverse bias mode. So SCR during the reverse bias mode, it will not allow the current. So that's why SCR
Yes, sir.
will definitely block that voltage. But what about the diode? Diode will be in the forward conduction mode. So that's why diode will not allow the composite switch to block that voltage. So that's why operating point will not be here.
Okay, sir.
And similarly, you can check for the negative current, right?
Okay, sir. Yes, sir. Thank you, sir.
Okay.
Thank you, sir.
Hello, sir.
Yes, please. Yes, please unmute yourself, Salman Khan.
Hello, good evening, sir.
Yes, good evening.
I have a doubt in that switching operation, sir.
Just a minute, one by one. I think someone was asking. Yes, please go ahead.
Okay, sir. In the switching, sir, suppose means the switch is turning off, then current reduces and voltage increases, right, sir?
Please repeat.
When switch turns off, means
Your voice is actually too low. Will you please bit louder?
is it audible, sir? Now?
Yes, audible.
Yeah. When switch turns off, sir, the current reduces.
When
and
the switch
voltage
turns
increases.
off.
Off, right, sir.
Okay.
Current reduces and voltage increases, right, sir?
Yes. No. When the switch is turned off, you are saying
Yeah, off.
current reduces, voltage increases. Huh?
Yeah. But in some examples, we have seen that current reduces later, before that voltage reduces. How come that happens, sir?
Current reduces.
Later, before reducing the current, voltage starts increasing.
Okay. In some of the examples means you are saying in this case, just a minute. Let me open that one.
Question 6, numerical 6.
Numerical 3, no?
Maybe.
In this, na? No.
I mean, sir, an example. We have taken some examples, sir. Means.
Okay. Yes, this type of, na?
Yeah.
Voltage is non-zero, current is increasing. This
example.
type of
I'm not
question.
getting
Okay.
it,
It depends. Okay. If they give this type of means, it is like for the voltage to reduce, it is like some delay time is there.
Okay.
Okay.
It means practically.
Means it is not like a thumb rule that both should decrease at a time. Means both should start at a time. Means voltage starts increasing and current start decreasing. It is not like that. Okay.
How do we get there, sir?
How do you?
How do we get that delay and all, sir?
That depends on your device construction actually. It indicates, this indicates that T1 means nothing but for voltage, it is like a delay time. Okay, for voltage, it is like a delay time. Means it is taking some delay.
Okay, sir.
Right? It is taking some time to reduce. And in practice, actually, it happens like this. Let me tell you. In practice, there is some delay time is always present in the device characteristic. But in some of the examples, they neglect that delay time. Okay.
Okay, sir.
Right.
Okay, sir.
Sir.
Yes, please.
Good evening, sir. Regarding the quasi square wave problem that we did.
Just a minute. Quasi square wave. Yes.
That formula. Why have we taken half cycle instead of function total periodicity?
Okay. Because this is a pi, na, divided by pi.
Yes, sir. But naturally, we would have taken 2 pi.
No. For 2 pi, actually, it is like 0 to 2 pi means your one complete cycle's angle, na.
Sir.
And if when we derive it, it is like a divided by pi, na.
But for previous functions, we have taken the periodicity of the complete wave, no, sir.
Yes, because for the previous questions, if you check for this question, no, this is actually we have solved the logical, that is the. But if you consider this one, here it was like divided by t, na.
Sir.
So if it is t, so that's why I have written it is periodicity, because our periodicity is t, na.
Okay, in seconds.
Whatever we are writing here, it is related to this term.
Okay.
Right? In the quasi square wave, if it is like divided by 2 pi, then we need to consider the full angle corresponding to one cycle, right?
Yes.
Sir, once open composite slide, sir. Like last.
Manjuna, just wait. I still have doubts.
Okay. Fine.
Yes.
Sir, please continue.
Yeah.
And then in another question, I have another doubt. For a 600 volt 0 for a switch turn on process, 100 hertz triggering, find the P average loss of a switch.
Just loss of switch, no? This one?
Yes, sir. That one, sir.
In this,
why did we find energy loss first, sir? And we could have directly gone for power loss only. We could have done 1/t integral, and we would find.
We can go. But since we are having the expression for the energy loss, na, if it
Ah,
is
sir.
decreasing, if it is increasing, we are having one straightforward expression.
Okay, okay.
So that's why I am directly using that expression in order to save the time. That's it.
Okay, sir. That's it, sir. That's it. Thank you.
Okay. Yes, next.
Sir, once open last example, sir.
Just a minute. Last example.
Composite switch.
Yes.
Sir, here when voltage is positive, we are considering SCR is switched off, and when current is positive, we are considering SCR is switched on, sir.
Yes, tell me.
When voltage is positive, we are considering SCR as off, sir. And when current is positive, we are considering SCR as on, sir.
No, actually the thing is, our task is to identify the static operating point on VI plane, right?
Yes, sir.
So operating point on V axis, that is plus V or minus V.
Yes, sir.
It depends whether the switch is unipolar or bipolar, right?
Yes, sir.
And in the unipolar bipolar definition, we have discussed that we need to focus on which state, off state only.
Okay, sir.
So while finding the location of these 2 points, that is plus V and minus V, we need to consider the active switch in an off state only. Active switch, I am using the word.
Yes, sir.
Right? So
yes,
that's why I have considered here it is a off state.
Yes, sir.
Right?
Fine.
So that's, and while considering this plus I or minus I, we need to consider it is in a on state.
On state. Yes, sir. Fine.
Right?
Wonderful.
Okay. Next.
Sir, hello, sir.
Yes, please.
Sir, what is the meaning of forward blocking and reverse blocking, sir?
Okay. Forward blocking, reverse blocking, you will understand when we discuss that particular device. But anyways, I will give you an overview. Forward blocking, the meaning is a device is in a forward bias mode, but it is in an off state. Means in the case of SCR, if you check, when SCR is in a forward bias mode, and if we will not apply the gate signal to the SCR, whether the SCR will turn on, no, na?
Yes, sir.
So that's why it is forward blocking. And reverse blocking means in the case of diode, whether we are having the forward blocking mode, no, because diode is an uncontrolled switch, na? As soon as it becomes forward bias, immediately it starts conduction. In the diode, we don't have the forward blocking mode. In the SCR, actually the forward blocking or that forward conduction mode, we are having only in the active switches, in the controlled switches. Okay. And reverse blocking means when the device is in a reverse bias mode and it is in a off state. Right?
Okay, sir. Sir, again, one triggering frequency. What is the meaning? Can you again explain, sir? Triggering
Just a minute. Triggering frequency means triggering is nothing but your turning on. Okay. We're having a triggering methods, we're having turn on methods. Trigger is nothing but turn on. Okay. So triggering frequency means, for example, suppose triggering frequency is 100 Hertz. Means in 1 second, I am turning on my switch 100 times. That indicates the triggering frequency.
Sir, we are turning on means simultaneously we are turning off, sir. Then we have to consider both, no, sir.
Yes. We need to consider both means what? If unless and until it is turned off, we cannot turn it on again, na?
Yes, sir.
So here turn off means we need to consider it is turned off already. But in that numerical, actually, they have not commented anything regarding the turning off, na?
Yes,
so
sir.
that's why we haven't discussed it there.
Sir,
But we need to assume it is turned off somewhere, right?
If they give turn off time like that means then how to solve that problem, sir?
If they give turn off time, then we need to find the simple turning energy loss or the power loss during the turn on, power loss during the turn off, and then we need to find the total switching losses. In one example we discussed, na? Scheme 1, scheme 2 was there, I think.
Yes, sir. Yes, sir.
In this year, right? In this example, they are having turn on and turn off both.
Okay, sir.
And they have given the triggering frequency also in this switching frequency, na? The switching frequency is nothing but your triggering frequency in this case. Are you getting the point?
Yeah.
Means here our switch is turning on here. For this time it will be the on state. Again we are turning it off, and again after some time we are turning it on. But in 1 second we are turning on the switch 100K times. Can you imagine 100k times we are turning on the switch, right? Means our switch turn on and the turn off, that is the transition period is very, very small. It is given in the nanoseconds. You have checked, right? It is in the nanoseconds, means very small time is required. Okay.
Okay, sir, here switching frequency we want to denote means in this switching scheme 1 figure, sir. Can you move the slides?
In
Here
this,
switching frequency, where we will denote, sir.
okay. Switching frequency, actually they have not given it, but if we want to denote, it will be like this. Suppose this is the voltage. Let me draw the V and I on the same axis. Okay.
Okay, sir.
This is a time t, for example. Suppose initially, this is a turn on and next suppose turn off. Okay. So initially switch is in a off state, so the voltage will be high, right? Current will be 0. After that, voltage is decreasing because switch is starting turn on transition, right?
Yes, sir.
Just a minute. Yes. So voltage is decreasing. Okay. So till this time it will be 0 and current is here increasing. Okay. Let me show the current with a dotted line. And after this instant, this is your TR, na? Turn on time. This is your, let us consider it as a TF. That is switch is turning off, na, again. So when switch is turning off, the voltage will increase. And again, current will decrease. Okay. So now can we say that at this instant, it is like our switch has turned off. And if my switching frequency is 100 kilohertz, the meaning is, yes, this starting instant and the next starting time, the time difference will be like your 1 by 100k. Is this clear? Means after 1 by 100k, again the same cycle repeats.
Okay. It is like periodicity now, sir.
Yes, it is like a periodicity now, right?
Yes. Sir, thank you, sir.
Yes. Please, next.
Sir, in composite switch, sir.
Yes, Ravan, who is speaking?
Paul Vignesh.
Yes, please.
In composite switch, I have one doubt, sir.
Just a minute, a composite switch. Yes, tell me.
On that graph. Sir, here when the composite voltage is negative, SCR will block negative voltage also, sir, because it is bipolar device. Why you have not mentioned in the negative direction, sir?
Because check for the diode, na. Composite switch is not like only SCR. It is a combination of both.
Okay, sir.
When voltage is negative, means it is a plus here, it is minus here. Diode will be in the forward bias mode.
Okay, sir. And another one doubt.
Diode will block that voltage. No, na. Right?
Yeah, sir. Sir, another one doubt, sir, that switching scheme 1, scheme 2 question, sir.
Switching scheme 1, scheme 2. Yes, this example. Right.
Yes, sir. In these examples, in scheme 1, both are decreasing. So we are using this formula VITR by 6.
Correct.
Here you have taken voltage as 400 and current as 20 amps. But here it is decreasing now, sir. From 400 it is falling. How can you take that 400, sir?
No. The thing is, actually, we have derived this expression where, let me tell you. We have derived this expression already.
Yes, sir. I have that derivation.
Yes. Not this one. Let me tell you. Yesterday, na?
Yes, sir.
Yes. Transition behavior of the switch, right? This expression, na?
Yes, sir.
In this expression, what is this capital V and capital I? Here, capital V and capital I are nothing but capital I means this current, na?
Okay.
This voltage. So those voltages actually we are getting in the final expression, na? So that's why here we put those values only, right?
Yeah. Okay, sir.
Right. Yes.
Thank you, sir.
Hello, sir.
Okay.
Hello, sir.
Yes, please.
Sir, can you please show me BJT MOSFET SOA diagrams?
Just a minute. BJT MOSFET SOA. Yes, here. BJT MOSFET and here. Yes.
Yes, sir. Sir, is same as diode, sir. Sorry.
No, diode is in second quadrant.
Okay, okay. So
These three are in first quadrant.
sir, explain once BJT safe operating area.
No, for all these three, actually the thing is they are blocking the forward voltage and allowing the forward current only.
Yes, sir.
Right? So that's why the safer operating area is, yes, that is the combination of these two. So that's why it is a first quadrant.
If
You
these
understand
two
why the BJT is blocking forward voltage and it is allowing forward current while discussing the BJT. We have not yet discussed the operation of these switches, right?
sir, means it's allowing points, sir.
What?
These 2 points are maximum allowing points, sir.
Yeah, maximum allowing voltage and maximum allowing current.
Acha, okay, sir. And in combination switches, diode conducting point, explain once.
Composite switch. Right?
Composite switches. Yes, sir.
Yes, here it is.
The below points are diode conducting point.
Okay, here it is.
Sir, first combination diagrams.
What?
Composite switch characteristics, yes, sir.
You are saying composite switch characteristic. This one?
Sir. Below point, sir.
This one.
Diode conducting. This one, please explain.
Okay. Now, what this point indicates?
Maximum.
This point indicates current is negative, voltage is 0. The meaning is our composite switch is allowing the negative current.
Yes,
so you can check if the negative current is flowing, that is negative current means current is flowing from B to A.
Yes, sir.
So whether the negative current will be allowed for our composite switch, we can check. Definitely our thyristor will not allow the negative current.
Yes,
but whether our diode will allow it, definitely diode will allow it now, because when B is positive, A is negative, it is like diode will be in the forward conduction mode.
Yes, sir.
So that's why diode will allow the reverse current, that is B to A. So that's why here we'll be having the operating point location.
But it is happen when voltage with respect to diode anode is positive, sir.
No, you cannot. Yes, you can say that, because when voltage is B is positive and A is negative, then and only then the negative current will flow. Na? For circulation of current, the thing required is we require a voltage.
Sir.
Right? The meaning is this is having actually two meanings. One is if B is positive, A is negative, our switch is not blocking the negative voltage. Switch is not blocking the negative voltage means what? Negative voltage will not be there in our switch characteristic. Okay, that is the static operating point. So corresponding to this, again we are having the voltage is 0. This point corresponding to this point, current negative, voltage is 0. Right? That is nothing but diode is in the conduction mode.
Instead of anode positive, we consider as negative voltage, sir.
Instead of
diode anode is positive, is as considered as negative voltage.
I am not getting what you are saying. Please repeat once.
Diode anode is positive, no, sir. Instead of
diode anode is positive means what? Your B is positive.
Yes, sir.
If B is positive and then diode will be in the forward bias mode.
Yes, sir.
So that's why the current will be flowing here.
Yes, sir.
So that's why here the negative current will be flowing.
For overall composite switch has negative voltage allowing, sir.
Negative current I am saying.
Negative current.
Negative voltage allowing you cannot say. We don't have the concept like voltage allowing. We are having the concept like voltage blocking and the current allowing. This type of concept we are having.
Okay, sir.
Right? We are having the positive current as well as negative current allowing and the positive voltage blocking.
Okay, sir.
Right? Okay.
Oh, thank you.
Yes.
Sir, once open MOSFET with body diode slide, sir.
Just a minute. Let me for other participants also let me unmute. Shravan Kumar, Akshay. Just a minute. One by one, please ask the questions. Which you are saying?
MOSFET with body diode slide, sir.
MOSFET with body diode. Yes, here.
Sir, once explain that graph, sir.
This one, na? Okay. Yes. Actually, the thing is here to have not discussed anything about the MOSFET, right? But in the MOSFET, we have discussed in the previous page. If you check, yes, here we have written the MOSFET here, right?
Yes, sir.
And the MOSFET is like it is allowing the forward voltage and the forward current, right? Positive voltage it is blocking, and it is allowing the positive current. Okay.
Okay, sir.
Now this will be there, no problem. But if you check the MOSFET with body diode here, whether our diode, this diode is there, na?
Yes,
So
sir.
whether this diode will block the negative voltage. Negative voltage means it is like okay, minus here and plus here.
Yes, sir.
Sorry, negative means opposite actually. This is a minus. Let me show minus here and plus here. So whether this is plus, this is minus, whether our diode will block that voltage? No, na? Diode will be in the forward bias mode, so diode starts conduction. So that's why this current is like for our switch, this current is like the negative current, na?
Yes,
So
sir.
that's why it is allowing the negative current. And whether it will block the reverse voltage? No, for the reverse voltage, diode will be in the conduction mode, so it will not block the reverse voltage,
Okay, sir.
right?
Okay, sir. Sir, IGBT with body diode.
IGBT with body diode. Okay, same thing,
Yes, sir.
right?
Yes.
Positive current means collector to emitter. Negative current means emitter to collector. We'll discuss these points again while discussing the IGBT. Okay. Here for only considering this, I have shown as a summary here. Okay.
Okay, sir. Thank you.
Okay.
Hello, sir.
Yes. Yes, please.
Sir, when calculating power loss in on-state and conduction losses, sir, conduction state.
Power losses in
Numerical problems, sir.
Yes, here it is.
No, sir. First, we are discussing
This
first
one?
numerical. No, sir, not this, sir.
Which-
During on-state and conduction state losses, sir.
This is not scheme 1, scheme 2.
No, sir. Means when we are considering DC voltage and resistance.
When we are considering
DC voltage, sir.
okay, means
Voltage.
you are saying that modeling.
Yes, yes.
Piecewise modeling. Okay. Here, yes. On state power loss. Yes.
Yes, sir. We are considering when we are means one problem is there now. We are considering both the DC and resistance.
DC and RMS.
Yes, sir.
Why? Because the thing is, if the device is modeled as only register,
yes, sir.
then we have written P on, we have derived, na? P on is equal to what? RMS current square into R on.
Yes, sir.
If device is modeled as only voltage drop,
Yes,
then
sir.
it is like a voltage drop into I average. And if the device is modeled as R on and VT,
yes, sir.
then we need to take here as RMS square, current square into I0, I average into V2, this type.
Sir, at that time, both the losses sir, device consider. We are
Yes,
considering.
this total losses is nothing but the device losses only.
Yes, sir. At that time, device.
Because the R-on is not the external register we have connected.
Yes.
R-on is a register of that device which is present in that body only. Due
Yes,
to its
sir.
characteristic that R-on is there.
Yes, sir. During turn on and conduction, both.
Yeah.
And
If-
that period, both periods, we have both losses at that time only.
Yes, only during the conduction period.
Okay, sir.
Right?
Yes, sir. Conduction period only we are considering on-state losses and conduction losses both, sir.
Yeah, on-state losses means your conduction losses.
Okay, sir.
On-state means what device is in a on-state, and
Yes,
conduction
sir.
means what device is in a conduction mode. So on-state losses and conduction losses both are having the same meaning.
Okay, sir.
Right?
Yes, sir. That's all. Thank you, sir.
Okay. Yes, next.
Hello, sir.
Yes, please.
Sir, in quasi square wave and square wave, and all, we have like found the RMS value, but
Just
what about the
quasi square wave.
That section where we found the RMS value of the wave, right? Yeah, for
In the RMS value expression, huh?
sir, not in that, but like for these cases, what about the average value of the wave?
What is the average value, na?
Yes.
Okay, okay, okay. The average value is actually its average value will be 0. How to find the average? That is the average of this one plus average of this one.
Yes, sir.
Now you can check whatever the positive pulse we are having, the same negative pulse is there, na?
Yes, sir.
This pulse width is like alpha to pi, so pi minus alpha.
Yeah.
This pulse width like pi plus alpha to 2 pi, so total pulse width is 2 pi minus pi plus alpha na bracket. So that's why it is like pi minus alpha. So equal values, na? Equal pulse width and values are opposite. So that's why its average and its average will be same values but negative. One is negative, one is positive. So resultant average will be 0. So that's why we have not considered it.
Okay, sir. Sir, then one more
Similarly,
thing.
you can check for that also. Now we can
Sure.
find, even if we require, we can find it. This is also 0 to pi, it is a positive, pi to 2 pi negative. Na? Same
sir.
pulse width we are having. Same here it is A, here it is minus A. So average will be 0.
0. Yeah,
Right?
correct.
Yes.
Yes, sir. Sir, then one more thing, that conduction and switching loss. For conduction loss, we have both on-state loss and off-state loss, but the off-state
No,
loss
no,
is
no. Conduction loss means on state loss only.
okay.
And switching loss is nothing but transition period loss. That is turn on transition, turn off transition, right?
Okay, sir. Sir,
So
then
switching-
what about off-state power loss? You mentioned that
No,
earlier.
no. Actually, the off state power loss is during the off state. Actually, the current flowing through the device is very small, na?
Oh, yeah.
It is in the range
So
of microampere. So
we
therefore, if
can
you check the
neglect that.
microampere current into that voltage,
Very
that will
small.
be very small value, negligible.
So it doesn't fall under conduction loss. So,
Yes, yes.
so that off-state power loss is a separate thing and it doesn't fall under conduction loss. So is that
Off
correct?
state power loss is
Not a subsection of conduction loss. So is that correct or?
will you please repeat? I am not getting means
Oh.
only half per statement. Actually, I am.
Okay, sir. So like if we say conduction loss, then that means only the on-state power loss, and
Yes.
the off-state loss is not at all related to the conduction loss.
Yes, yes. Off state loss means what? When device is in off state, whatever the loss is. But if till now they have not asked the question. But suppose if they ask the question and if they give that the current flowing to the device during the off state is so and so microampere, and voltage across the device is let us consider 200 volt, then what will be the power loss? We can find the V into I, simple thing.
So
But so far they have not asked because generally we neglect it. It is a very small amount, na?
okay, sir. Then about switching loss, like if suppose one question they ask find switching loss and we are given the turn on time and turn off transition, both transitions are there, then we should find both and add and give the answer.
Yes, we should find both and then we need to add.
Only if only one is there, then find only for that and give the answer. right?
Yes, yes, definitely correct.
Sir, then one more doubt from last class, we had practical switch SOA, right? We drew the
In the last class,
practical switch SOA, safe operating region, we drew the characteristic, right? Thermal stability.
yes, that was there. Just a minute. I think here it is only there. Yes, yes, in that.
In that, I just wanted to clarify that the SOA, is it the inner dotted rectangle or is it the outer rectangle minus the small four corner area?
No, generally the that SOA, okay. The thing is like this cross section, right? This cross line.
Yeah.
And here, whatever the solid line is there, na?
Yeah.
That will be your SOA. But according to the manufacturer, he suggests that this the dotted rectangle, okay, it will be better to keep into the dotted rectangle.
Okay, okay.
Right?
Yes, sir. Yes, sir. Got it, sir.
Theoretically speaking, only this one, that is the solid line and that cross line, power limit line.
Okay, okay, sir. Yes, sir.
Right?
Got it, sir. Thank you, sir.
Yes, next.
Hello.
Yes.
Hello, good
Karthik,
evening.
Right?
Hello, good
Good
evening,
evening.
sir.
Good evening. Good evening.
Sir, I had a doubt regarding quasi square wave, sir.
Just a minute. Quasi square wave. yes, I think here it is. Yes.
So, while writing the shortcut formula, we had taken the function duration as pi minus alpha, sir.
Okay.
But while considering positive and negative half cycles, it would come like 2 pi minus 2 alpha.
No. Actually, the thing is here the function is nothing. This is the one function.
So, but
Function.
time
Okay,
period
so
is from
function
0
duration
to
is
2
this
pi.
one actually. This is a function duration. And total time period, that is total one cycle angle is 2 pi.
Sir, I understood that formula, sir. If we take a half period, then it will come like pi minus alpha by pi.
Where here, na?
Yes, sir. If it took function duration as 2 pi minus 2 alpha, that in denominator we can write 2 pi, sir. Then it would become a full cycle angle.
Yeah, both will be having the same meaning.
Yes, sir.
2 into pi minus alpha divided by 2 pi, right? You are saying 2 into
Yes,
pi
sir,
minus
yes,
alpha
sir.
divided by 2. Both are having the same meaning.
We could write anything
Right?
we want.
Yeah, anything you can write. The only thing is, in order to save the time, okay, instead of this, I have given this formula.
Okay, sir. That's why
Directly you can use it. Okay.
Yes, sir. Again, I just downloaded a CRO PDF, sir, but it is showing the CRO questions of power system, sir.
CRPQ, that is classroom practice question PDF.
Yes, sir.
Okay. Let me check with the Seshu actually. I don't know what he has done. Those office people only they have uploaded. I will check with them. Okay.
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 Thank you, sir. Thank you.
Yes. Thank you. Yes. Next. Sirisha, Shravan Kumar, do you want to say something? Yes, Chintak. Yes.
Sir, this is Tejas.
Yes, please.
Sir, in IGBT with body diode,
Okay.
so there in the SOA,
Yes.
so the point on x-axis, that means that is the maximum voltage it can bear, right? So maximum blocking voltage.
Yes.
So it is a maximum blocking voltage. So the left hand side also will come under the shading part now, sir. But why we didn't share the LHL side?
Miss, here you are saying.
Yeah, yes.
Because when this voltage is negative, this voltage is negative means here it is plus, here it is minus, right?
Yes, sir.
So whether this body diode will be in the forward bias mode in this case?
Yes, sir.
Because E is plus, C is minus means anode of the diode is positive, cathode is negative. So diode will be in the forward bias mode.
Yes,
So
sir.
diode will directly become short circuit, na?
Yes, sir.
So that's why that negative voltage will not appear here.
So safe for operating area means in that area our devices won't get damaged, right, sir?
Yeah, device won't get damaged, but in this case, if you check with the body diode, in this case, that negative voltage will not appear at all across the device. Because directly it will be getting short circuited.
Yes.
The thing is that will be negative when, when our device will be in the off state during the reverse bias. But whether this diode will allow our device, that IGBT with body diode, our diode will allow the device to remain in the off state during the negative voltage? No, na?
No, sir.
Right? Simply diode will be in the conduction mode.
Okay, if it is in conduction mode, it is not necessary to mention in SOA.
Yes.
Okay, sir.
Because if you mention here, then it is like we are saying that our IGBT with body diode is like a bipolar switch. No, but it is not a bipolar, na?
Yes, sir, it's not.
Yes.
Thank you.
Yeah.
Good evening, sir.
Yes. Please.
Good evening, sir.
Good evening.
Sir, small doubt in composite switch. The
yes.
SCR is considered in off state. Can you repeat that again? why it is considered in off state while
Just a minute. Just a minute.
composite
Yes, composite
switch.
switch here, huh?
So the SCR SOA, I mean how SCR SOA is considered. Can you repeat that?
Okay, yes.
In
So
the
here,
overall.
this point, yes, this point indicates
Yes, sir.
voltage is positive.
Yes, sir.
Voltage across SCR is positive,
Yes,
but
sir.
current is not flowing. The meaning is SCR is in a forward bias mode, but
Yes,
we
sir.
have not applied the gate signal. So it is like
Okay.
SCR will be in the forward blocking mode. So when
Yes.
SCR is in a forward blocking mode, whether it will allow the current? No.
No.
So definitely it will block this voltage now.
Yes.
Now suppose SCR is in a forward blocking mode, and now I am applying the gate signal. So what will happen? Definitely our SCR will turn on.
Yes, sir.
As soon as SCR turns on, positive current will be flowing through the SCR. So
Yes,
that's
sir.
why here plus I is there. Are you getting the point?
Okay.
And suppose when the voltage across the SCR is negative, then whether SCR conducts in the negative, that is reverse bias? No, na?
No.
So it will be like open circuit only. So that's why the point will be here.
Okay, so it will block the negative voltage.
It will
also.
block the negative voltage, right?
Okay, thank you.
Okay. Yes. Yes. Next. Sirisha, do you want to say something? Shravan Kumar, you have raised the hand.
No, sir, nothing, sir.
Okay. Thank you. Thanks to all of you.